Imagine rewinding a dashcam footage spanning 10 million years, only to discover that every intersection, every turn, every possible road leads nowhere, nothing but an endless, untraceable expanse. This bewildering image encapsulates what astronomers encountered when they attempted to trace the origins of the third confirmed interstellar visitor ever observed. In July of 2025, a streak named 3IATLAS surged through our inner solar system, capturing the attention of scientists worldwide. Within mere weeks, major observatories, Hubble, James Webb, and numerous ground-based telescopes focused their instruments on this mysterious object. The standard approach would have been straightforward: retrace its orbital path, identify its parent star, and map its gravitational journey through the galaxy. But what emerged was a startling void, a cosmic dead end. Decades of searching revealed no meaningful encounter with any star, no gravitational fingerprint, no signature of a birthplace. Its chemistry defied expectations, with dust particles behaving in ways we've never cataloged before, and its motion suggested it had been drifting through space long before our sun ignited, perhaps since the dawn of the galaxy itself. Stay with us until the end, because we're about to explore why this object unsettles scientists who study origins, and what it signifies when an interstellar visitor refuses to reveal the most fundamental question of all. Where did it come from? Part 1. 3IATLAS as a ghost. Let's set the scene. On the first day of July in 2025, the Asteroid Impact Alert System stationed in Chile detected a swift streak slicing through the inner regions of our solar neighborhood. Within hours, astronomers realized they were witnessing only the third confirmed interstellar object to pass through our vicinity. They dubbed it 3IATLAS, though for simplicity during this narrative we'll call it simply Atlas. Scientists around the globe immediately directed their most powerful telescopes, space-based observatories like Hubble and James Webb, alongside terrestrial telescopes from Hawaii to South Africa, aiming to capture every detail. Naturally, once an interstellar wanderer is spotted, the instinct is to trace its origin. The usual procedure: rewind its path through the galaxy, identify which star might have ejected it, and reconstruct its gravitational history. Here's where things took an unexpected turn. A team led by Perez Couto published a study in 2025 aiming to do just that, an exercise as routine as it was critical. They employed Gaia Data Release 3, the most precise stellar census ever assembled, which mapped millions of stars in 6 dimensions. Position, proper motion, distance, and velocity. Using this treasure trove, they simulated Atlas's trajectory backwards over 10 million years, testing it against every nearby star in the database within a cone spanning 500 parsecs, roughly 1,600 light-years across. They identified 93 candidate stars that might have come close enough to gravitationally influence Atlas, nudging it onto its current hyperbolic path. Yet astonishingly, every single one of these candidates proved to be a dead end. Not a single star showed a meaningful perturbation. The closest star, catalogued as Gaia DR 36863591389529611264, passed within roughly 0.3 parsecs, about 98,000 astronomical units, and at a relative speed of 35 kilometers per second, which is quite swift. However, when calculating the gravitational impulse, the tiny push exerted during such a flyby, the resulting velocity change imparted to Atlas would have been approximately 5 times 10 to the negative 4 meters per second. In more familiar terms, that's about half a millimeter per second, an effect so minuscule that it's effectively negligible. It is orders of magnitude too small to explain how Atlas ended up on its current trajectory. This presents an extraordinary paradox. Atlas's orbit is unmistakably hyperbolic, confirming its extragalactic origin. Yet, when scientists searched for its ancestral star, they found nothing. No star that could have ejected it, no gravitational signature, no stellar sibling or parent system. It is a cosmic orphan, drifting through the galaxy without any apparent home. To emphasize, this isn't simply a matter of incomplete data. The team ran thorough searches, accounting for measurement errors, uncertainties in orbital parameters, different reference frames, and statistical variations. Even with extensive Monte Carlo simulations, drawing hundreds of slightly varied trajectories, the results remained consistent, no identifiable origin. The trail has gone cold. Interestingly, despite its high peculiar velocity relative to the local standard of rest, the average motion of stars in our neighborhood, Atlas's movement appears consistent with the thin disk of our galaxy. When plotted in galactic coordinates, its velocity components fall within the distribution typical of relatively young stars that populate our neighborhood. It doesn't resemble a halo interloper from the galaxy's ancient outskirts. It looks, kinematically, like it belongs here. But if it's from here, why can't we find where? The discovery itself triggered a global observational campaign. Atlas, spotted in Chile. That velocity, merely 0.5 millimeter per second, might seem negligible, yet it is astronomically insignificant when considering how Atlas arrived at its current trajectory. Orders of magnitude smaller than what would be necessary to account for its path. Let me present the paradox in the simplest terms possible. Atlas follows a hyperbolic orbit, which unequivocally indicates it originated from outside our solar system. This much is certain and not up for debate. Interstellar objects like Atlas do not appear out of nowhere. They must have a source, a birthplace somewhere in the galaxy. However, when scientists diligently search for that origin point, they come up empty-handed. There are no gravitational footprints, no telltale signs of a parent star, no stellar sibling that could have ejected it into its interstellar voyage. Atlas is essentially a cosmic orphan, a solitary traveler with no apparent lineage in every dataset or catalog we possess. And before you assume that perhaps our searches are simply limited by insufficient data, consider this. The team conducting these investigations employed the most rigorous methods available. They used Monte Carlo simulations to sample orbital uncertainties, accounting for the covariance ellipsoids, measurement errors, and all the complexities involved in tracing an object's history. They checked multiple reference frames, cross-referenced different traceback studies, and employed every analytical tool at their disposal. Despite this exhaustive effort, the conclusion was unwavering. There is no identifiable origin point. No star, no host system, nothing to trace Atlas back to. The data consistently points to the same conclusion. It has no known source. What makes this mystery even more intriguing is a seemingly paradoxical detail. Despite Atlas moving through our neighborhood with a high peculiar velocity, meaning it's moving significantly faster relative to the local standard of rest, it appears kinematically consistent with the thin disk of our galaxy. When scientists plot its motion in galactic coordinates, run diagrams, and perform likelihood diagnostics, Atlas's trajectory aligns with the movements typical of relatively young stars in our vicinity. It's not behaving like a halo interloper from the galaxy's ancient outskirts, nor does it seem to be an ancient relic from a bygone era. Instead, it moves as if it belongs somewhere close by, perhaps even formed here. But here's the perplexing part. If Atlas truly originated from this region, why are we unable to locate its birthplace? The discovery itself set off a global observational campaign almost immediately. Atlas was first spotted by the Chilean Atlas survey, then targeted by the Hubble Space Telescope. The James Webb Space Telescope turned its infrared gaze toward it, and observatories from Hawaii to South Africa monitored it nightly. It was not a faint smudge barely distinguishable in a single data set. It became one of the most intensely scrutinized objects in the sky in a matter of days. Despite this high level of attention and an abundance of data, we find ourselves at a fundamental impasse. We still cannot answer the most basic question anyone would ask about any object. Where did you come from? To grasp the significance of the term untraceable, it's crucial to understand that this isn't a matter of scientists shrugging their shoulders in uncertainty. It's not an admission of ignorance, but rather an indication that they have looked for the trail and found nothing. Imagine watching a dashcam video of a car passing through intersections over millions of years. You're asked to rewind the footage to find the last turn the vehicle made before entering your frame of view. You rewind by seconds, then minutes, then hours. As you go further back in time, the roads start to blur. Intersections smear into each other. Lane markings fade into noise. When you rewind all the way back 10 million years, the car is still on the road, but every intersection and exit ramp you check is nowhere near where the car supposedly came from. The trail has simply vanished into chaos, lost in the turbulence of countless small perturbations and cosmic noise. For the field of interstellar object research, this is more than just an intriguing puzzle. If Atlas cannot be linked to any parent system, then the entire effort to map galactic chemical evolution through these wandering rocks hits a proverbial wall. The overarching goal was elegant: capture an interstellar comet, analyze its composition, trace its orbital history back to its stellar birthplace, and thereby piece together the chemical evolution of planetary systems across the galaxy. But if the initial step, tracing its orbit back, is impossible for reasons we cannot currently understand, then this grand plan faces a significant setback. The concept was ingeniously straightforward: intercept an interstellar comet, analyze its chemical makeup, and then trace its orbit backward through space to identify its parent star. Once the star is pinpointed, its age and metallicity could provide a timeline for when the comet originally formed, allowing us to piece together a chemical map of planetary systems scattered across the galaxy. This approach promised a revolutionary way to understand the distribution and characteristics of exoplanetary environments, one wandering rock at a time. However, this elegant plan hinges critically on the initial step, successfully retracing the comet's trajectory to its stellar origin. And here lies the crux of the problem. What happens if this fundamental starting point fails? If, for reasons we have yet to fully comprehend, the orbital traceback cannot be completed, then the entire map-building exercise hits a dead end. I must emphasize, with a note of caution, that untraceable does not necessarily mean forever untraceable. It simply indicates that given our current tools, datasets, and methods, the trail remains elusive. Future advancements, more detailed and precise data, may yet fill the gaps. Upcoming releases of Gaia data, for instance, hold promise. They could offer improved astrometry, sharper measurements of stellar positions and motions, thereby tightening the uncertainties that currently hinder precise orbit reconstruction. New catalogs cataloging the proper motions of fainter, less luminous stars might also reveal potential parent stars that have so far gone unnoticed. The universe does not hide its secrets out of spite or malice. Rather, it does so because our eyes and instruments are still imperfect. It's a matter of technological progress, our evolving, ever-sharpening vision, rather than some cosmic conspiracy. Yet as matters stand today, with the very best data available, Atlas appears to have no identifiable ancestral star in our catalogs. And this realization is unsettling, reaching beyond mere ignorance to touch on a profound philosophical issue. If we cannot, through current dynamical methods, trace its origins, then perhaps we should ask whether we can infer its birthplace through its composition, its chemistry. When orbital mechanics cannot reveal where Atlas came from, maybe the answer lies in what it is made of. This brings us to the next logical step in our investigation. If the dance of celestial mechanics refuses to disclose its secrets, then perhaps the molecular and elemental signatures in Atlas's coma and dust could provide a clue. Because when James Webb Space Telescope pointed its spectrograph at Atlas in August of 2025, what it observed was startlingly strange. The gases emanating from the object, the coma, the cloud of sublimating ice, did not conform to what we typically see in known comets. The chemical composition was unlike anything expected, hinting at an origin story far outside our usual understanding. This chapter of the investigation we might call the failed ancestry search, and I am going to walk you through it with precision. This isn't some vague speculation or hand-waving. It's a meticulous forensic endeavor that involves billions of potential suspects, stars, and a timeline stretching back 10 million years or more, to a period when our ancestors were still wielding primitive stone tools. The method resembles that of a detailed crime procedural, only the crime scene is a vast, ancient star field, and the suspects are countless stars that may have ejected Atlas long ago. The first step involved extracting high-quality six-dimensional data from Gaia's third data release. This catalog does not merely record where stars appear on the celestial sphere. It catalogs their precise positions, their proper motions in two spatial directions, their parallaxes, which give us their distances, and their radial velocities, how fast they're moving toward or away from us. Each star is quantified with 6 parameters, providing a comprehensive snapshot of its state in space and motion. To ensure the reliability of the data, the team applied strict quality filters. They only included stars with a parallax exceeding 2 milliarc seconds to focus on relatively nearby stars. They also filtered for the renormalized unit weight error, RUWE, to exclude measurements with excessive uncertainties requiring it to be less than 1.4. Additionally, they mandated at least 8 separate observational periods to avoid artifacts caused by transient measurement errors. After these rigorous cuts, they were left with a database of approximately 3.5 million stars, each with full radial velocity data, potential candidates for Atlas's stellar parent. The next step involved establishing the current initial conditions for orbital reconstruction. To do this, the team needed to know precisely where Atlas was now and how fast it was moving. They used the pre-entry heliocentric state vector, and set of coordinates and velocities measured relative to the Sun, calculated by De La Ente and colleagues in 2025. This vector provides a snapshot of Atlas's present position and motion from the Sun's perspective. However, to trace Atlas's orbit through the galaxy, these heliocentric measurements must be converted into galactocentric coordinates. Measurements referenced from the center of the Milky Way galaxy itself. To accurately trace the origin of Atlas, researchers had to consider the motion of our Sun relative to the local standard of rest, the average velocity of stars in our immediate neighborhood. This step is essential because any miscalculation here would lead to a significant shift in the entire backward reconstruction of Atlas's trajectory. Fortunately, they executed this step with precision, ensuring that the Sun's motion was correctly calibrated, laying a solid foundation for the subsequent analysis. Once that was established, the next critical step was to select a comprehensive model of the Milky Way's gravitational potential. Unlike a simple point mass, the galaxy is a complex dynamic system, a swirling disk of stars, a dense bulge of older stars at its core, and an expansive halo of dark matter enveloping everything. To faithfully simulate the paths of Atlas and potential parent stars over millions of years, it was necessary to use a model that accurately represented all these components. The researchers employed MW Potential 2022, which is among the most sophisticated galactic potential models available today. They utilized a software package called Gaia to perform the orbit integrations, calculating how the galaxy's gravitational forces would influence the movement of Atlas and every nearby star considered. This process involved stepping back through time, 10 million years into the past, meticulously computing how the gravitational pull of the galaxy would have affected the trajectories of these objects. But here's where the analysis becomes particularly challenging: the uncertainties involved in the orbital data. We do not know Atlas's exact current position and velocity with perfect precision. Small errors in these measurements today can amplify dramatically over such vast timescales, leading to enormous uncertainties when reconstructing its past path. To address this, the team didn't rely on a single trajectory. Instead, they employed a statistical approach called Monte Carlo sampling, drawing hundreds of slightly varied versions of Atlas's orbit from the covariance ellipsoids, mathematical representations of the measurement uncertainties. Each of these simulated orbits was consistent with the observational data but differed enough to account for possible errors and chaotic effects in orbital mechanics. They then examined each of these trajectories to see if any resulted in a close encounter with a star, potentially indicating a parent. Any star flagged as having come within a sufficiently small distance from Atlas in these simulations would be considered a candidate parent star. Despite the extensive sampling and generous allowances for chaos, the results were telling. Not a single plausible encounter emerged as a likely origin point. To put this into perspective, the study identified 93 nominal encounters within a 2-parsec radius, and of these, 62 passed at least a 2 sigma significance threshold, meaning they seemed statistically noteworthy. At first glance, this might seem promising, suggesting many opportunities to find a star that could have ejected Atlas. However, when the team calculated the actual energy transferred during these close approaches, specifically the change in velocity or delta V, the numbers were negligible. The strongest encounter, involving the star Gaia DR3 68 триллионов 600, 35 миллиардов 900, 13 миллионов 800, 95 296, resulted in an imperceptible velocity change of about 5 times 10 to the negative 4th meters per second. Less than a human walking imparts to surrounding air molecules. Why is such a tiny velocity change significant? Because gravitational influences scale inversely with distance and directly with relative velocity. When two objects pass by each other at high speed, the interaction is fleeting, leaving little time for meaningful momentum transfer. Think of trying to catch a baseball while riding past it on a motorcycle at highway speed. Your hand can only be near the ball for a fraction of a second, imparting negligible force. The same principle applies here. Only the star, Atlas, the baseball, and the highway, the Milky Way, are involved. The rapid passage doesn't allow gravity enough time to do much. Other teams, such as those led by Go and colleagues in 2025, conducted similar studies but used slightly different initial conditions and applied various corrections for parallax systematics. This resulted in encounter tallies that differed somewhat from Perez-Couto's findings. Nonetheless, despite these variations, the core conclusion remained unchanged. No star came close enough and imparted enough energy during its passage to plausibly have been Atlas's parent. In other words, after rigorous multifaceted analysis, the data offered no evidence of a specific stellar encounter that could explain Atlas's current trajectory. The search for a definitive origin star, therefore, ends in silence. There simply is no evidence of a close or plausible flyby that could explain Atlas's current trajectory. The discrepancies we observe are not in the broad conclusion itself, but in the finer details, those subtle variations that can often be attributed to differences in analytical approaches. When we carefully reconcile these differences, taking into account the specific choices of reference frames and the nuances of covariance sampling, the overall narrative remains consistent. Atlas is an orphan. It has no identifiable parent star or stellar system attached to its journey. This raises an intriguing question. Why do we limit our search to just 10 million years into the past? Why not push the boundaries further? There are two principal reasons that curb us at this temporal horizon. The first is chaos. Stellar orbits are inherently sensitive to tiny perturbations, and the orbital paths of interstellar objects are no exception. Over extensive periods, these paths diverge exponentially. Even minuscule gravitational nudges, such as passing stars, molecular clouds, or the galactic tide, compound over time, distorting the original trajectory beyond recognition. As we look further back, the integrative models become less reflective of actual history and more a jumble of noise, an unreadable record of a past that no longer exists in any meaningful, retraceable form. The second reason pertains to our current catalog limitations. The data from Gaia, which is essential for retracing stellar motions, becomes increasingly sparse beyond approximately 500 parsecs. Most stars in our galaxy lack measured radial velocities altogether, a crucial component for dynamic calculations, even if Atlas originated from a star 2,000 parsecs away. The absence of comprehensive radial velocity data would prevent us from verifying or reconstructing its origin. Consequently, 10 million years represents the practical boundary where traceback attempts still hold scientific value. Beyond that, we are essentially fishing blindly in the dark, unable to distinguish signal from noise. Now, what does it imply that Atlas's velocity components, its U, V, and W, are consistent with the galactic thin disk? When we map its motion through the galaxy, we find that these components fall comfortably within the distribution typical of relatively young stars in the disk. It does not behave like a halo star, which would have a highly eccentric inclined orbit and a much higher velocity relative to the local standard of rest. Instead, its kinematic profile suggests a connection to the disk population, which is generally younger and more metal-rich. However, this does not mean Atlas's age or chemical richness can be conclusively determined from its orbit alone. Membership in the thin disk is a statistical characteristic, not a precise biography. It rules out some exotic origins, like Atlas being an intergalactic traveler or a relic from the galactic halo, but it does not specify its exact formation environment. We have now reached a boundary where dynamics alone cannot provide a definitive answer. The orbital traceback, our primary tool for uncovering Atlas's past, yields no further clues. We have examined the data as far back as possible, checked countless stars, and accounted for uncertainties, yet the trail remains cold. Perhaps, though, Atlas might reveal some insight through its physical properties, something its motion cannot convey. Because Atlas isn't merely a silent rock, it is active. It is outgassing, wrapped in a coma of sublimating ice and dust. When James Webb Space Telescope turned its infrared spectrograph toward this object in August of 2025, it observed something profoundly peculiar, something that defies our current understanding of cometary composition. The data revealed a coma dominated by carbon dioxide, CO2. The spectral signature at 4.3 microns, corresponding to the CO2 vibrational band, was intensely strong, unmistakably indicating an abundance of CO2. Alongside that, Webb detected water, carbon monoxide, and tentative signs of carbonyl sulfide, as well as absorption features consistent with water ice and dust. Yet what stood out most was the sheer volume of CO2 present, a finding that introduces the so-called CO2 coma paradox. The ratio of carbon dioxide to water in Atlas's coma measures approximately 7.6, with an uncertainty of plus or minus 0.3. This ratio places Atlas among the most extreme cases ever documented in any comet, marking it as a remarkable outlier in the cosmic record. For comparison, the vast majority of long-period comets, as well as those belonging to the Jupiter family, typically exhibit CO2 to water ratios well below 1. In these familiar cases, water overwhelmingly dominates the volatile composition, with CO2 merely present as a trace component. However, Atlas defies this norm, inverting the usual chemical hierarchy. Here, CO2 emerges as the prevailing volatile overshadowing water, which now plays a subordinate role. This unusual chemical signature places Atlas in a very select and peculiar club, an exclusive subset of comets that display such high CO2 abundances. The only other known comet approaching this level of CO2 enrichment is C2V16 R2, popularly dubbed Comet Pan-STARRS or Pan-STARRS, which also demonstrated an unusually elevated CO2 content. Yet even Pan-STARRS was an outlier within a data set comprising hundreds of observed comets. Atlas's ratio far exceeds the norm. Its membership in this rarefied group signals that we are observing a comet with an extraordinary and perhaps unique chemical makeup. Adding to the intrigue is the morphology of Atlas's coma, the cloud of gas and dust surrounding the nucleus. Observations from the Webb Space Telescope reveal enhanced outgassing on the side that faces the Sun, a logical consequence of solar heating. Sunlight warms the surface, sublimating ice into gas that vents preferentially sunward. This creates a visible asymmetry, with more activity directed toward the Sun, consistent with expectations of solar-driven sublimation processes. Yet here is where the puzzle deepens. Despite the clear signs of activity and the pronounced asymmetry in the coma, there is no strong indication of non-gravitational acceleration affecting Atlas's orbit. In other words, even though Atlas's surface appears actively venting gas, its trajectory does not exhibit the subtle push, known as a rocket effect, that typically accompanies such sublimation-driven outgassing. We will explore this phenomenon in greater detail later, but for now it is important to note the paradox. Active coma, visibly enhanced on the sunward side, yet no detectable orbital acceleration attributable to outgassing forces. This anomaly is highly unusual and warrants careful consideration. What does a CO2-rich coma imply about where and how Atlas formed? In the context of planetary system formation, the presence of CO2 ice is a significant clue. Carbon dioxide ice has a frost line, the boundary beyond which it can condense, located farther from the star than water ice because CO2 is more volatile. In a protoplanetary disk, this frost line for CO2 typically lies beyond the water ice line. CO2 sublimates at lower temperatures, requiring colder regions for stable ice formation. Therefore, if Atlas is rich in CO2, it suggests that its origins lie in a colder zone of its parent system, likely beyond the CO2 frost line, or that it experienced some form of processing that depleted its surface water while preserving or even enriching its CO2 content. There are two plausible non-exclusive scenarios that could account for this chemical signature. The first posits that Atlas's nucleus is intrinsically rich in CO2. Perhaps it formed in the outermost regions of its planetary system, where CO2 ice was abundant and stable. Over millions or billions of years, its surface may have undergone radiation processing, transforming water ice into more complex organic compounds and leaving behind a relative excess of CO2. Additionally, it might have developed an insulating mantle, a layer of dust and refractory material, that kept water ice locked deep beneath the surface, while the more volatile CO2 could still escape from shallower layers. The second scenario relates to the thermal environment of the nucleus. When at a distance of roughly 3 to 4 astronomical units from its star, the Sun's heat may not penetrate deeply enough to reach buried water ice. In this case, CO2 with its lower sublimation temperature can vent from the shallower, more accessible layers, creating the appearance of a CO2-dominated coma even if the overall bulk composition contains more water. As Atlas approaches perihelion, the closest point to the Sun, at about 1.36 to 1.4 astronomical units, we expect to see water activity ramping up. If the CO2 to water ratio decreases at this stage, it would support the second picture, a thermal delay effect caused by the layering of volatile ices. Conversely, if the ratio remains high, it would favor the first picture, indicating an intrinsically CO2-rich composition. When comparing Atlas to another well-studied interstellar visitor, the comet known as 2I Borisov, differences emerge. Borisov, passing through our solar system in 2019, was characterized by a composition rich in CO, or carbon monoxide, rather. This points toward a formation environment that is distinctly different, one shaped by a thermal history unlike any we've previously encountered, or perhaps influenced by both factors simultaneously. What makes this particularly thrilling is the implication that each interstellar object we discover could serve as a unique sample, a messenger carrying the chemical signature of diverse planetary systems scattered across the galaxy. Such diversity enriches our understanding of the cosmos, revealing a tapestry of planetary formation conditions, compositions, and histories. However, this very variability complicates the task of constructing a cohesive, unified picture of what an interstellar object is supposed to resemble. Instead of a single archetype, we are faced with a spectrum of possibilities, each with its own story. As we prepare for the upcoming perihelion passage, when Atlas will come closest to the Sun, set for around October 29th or 30th, 2025, it becomes crucial to identify what signs to observe. Atlas will approach within roughly 1.36 to 1.4 astronomical units from the Sun, placing it just inside Earth's orbit, though not by a significant margin. If beneath a surface layer dominated by CO2, there exists buried water ice that has yet to reach a temperature sufficient for sublimation, the intense sunlight at perihelion should trigger a deeper penetration into the nucleus. This increased heating could cause water to start venting, leading to a marked drop in the ratio of CO2 to water in the coma. Such a change would be a compelling indicator of thermal processing, revealing that the current composition is at least partly a consequence of heating effects rather than inherent makeup. Conversely, if the CO2 remains overwhelmingly dominant even at perihelion, if water venting does not occur or remains negligible, that would point toward an intrinsic, genuinely unusual composition, not merely a thermal delay or superficial layering. In that case, Atlas might be exemplifying a class of objects with a fundamentally different chemical makeup, hinting at formation in environments vastly different from typical solar system conditions. Now I want to explore some speculative hypotheses, clear, cautious thought experiments rather than established science. These ideas are meant to stretch the boundaries of our thinking about Atlas's origins. For instance, could Atlas have formed in a circumstellar disk rich in carbon, perhaps orbiting an older star? Might it have condensed from material in a post-supernova cloud enriched in CO2 with its chemistry imprinted by such an environment? Alternatively, could it originate from a red dwarf system, where the snow line, the boundary beyond which volatiles like water and CO2 freeze, lies much closer to the star, skewing the volatile chemistry towards higher CO2 abundance? All these scenarios are plausible in theory, but current observational data do not provide enough evidence to favor one over the others. We lack detailed isotope ratios, such as deuterium to hydrogen or carbon minus trinazite to carbon minus vanazite, that would serve as fingerprints of its formation environment. Without these, we are left primarily with the observed chemistry, a CO2-rich coma. and an absence of a detectable parent star. As a result, chemistry functions as a breadcrumb, offering clues but no definitive solution. Here's the intriguing part. By combining the chemical data with the kinematic information, the fact that Atlas's motion aligns with the thin disk of our galaxy, we can begin to triangulate a potential origin that would otherwise be hidden from direct dynamical tracing. The motion's consistency with the thin disk suggests a relatively young, metal-rich environment. The dominance of CO2 hints at formation under cold conditions, possibly akin to a distant Kuiper belt analog in another star system, perhaps with a volatile composition that differs from our own. While this does not constitute a conclusive answer, it provides a valuable framework for interpreting the data, one that surpasses what we knew before Webb's observations. The coma's peculiarities extend beyond chemistry. When astronomers directed polarimetric measurements at Atlas, analyzing how light scatters off its dust grains, they encountered something extraordinary, an anomaly that defies the pattern seen in other solar system comets. This leads us into the realm of the polarization anomaly. Polarimetry, a technique that examines the polarization state of scattered light, might sound esoteric, but it is a powerful tool. When sunlight interacts with dust grains in a comet's coma, some of that light becomes polarized, meaning the electric field oscillates preferentially in a particular direction. The degree of this polarization and how it varies with the angle between the sun, the dust, and the observer encodes detailed information about the physical properties of the dust particles, their size, shape, porosity, composition, and surface texture. Over decades, astronomers have built a library of what typical solar system dust polarization looks like, establishing baselines against which anomalies can be identified. However, in the case of Atlas, the observed polarization properties are unlike any seen before. The measurements revealed a deep, narrow negative polarization branch, an unexpected dip below zero at small phase angles with a minimum of approximately minus 2.7% at about the degree of polarization observed in an object, specifically how this polarization varies with the angle between the sun, the dust particles, and the observer, serves as a diagnostic tool revealing crucial details about the dust's intrinsic physical properties. Every characteristic, whether it be the size of the grains, their shape, porosity, or chemical composition, leaves an identifiable mark, a unique signature in the polarization curve. Over many decades, astronomers have meticulously measured the polarization of light reflected off asteroids and comets within our solar system, gradually constructing a comprehensive catalog of what normal solar system dust looks like in polarization terms. This library acts as a baseline, a reference against which anomalous objects can be compared. When it comes to Atlas, however, the situation is markedly different. Early polarimetric observations, obtained using some of the world's most sophisticated telescopes, including the Very Large Telescope, the Nordic Optical Telescope, and the Roshan Observatory, reached phase angles between approximately 7.7 and 22.4 degrees. These measurements uncovered a feature that is highly unusual: a deep, narrow negative polarization branch. To understand why this finding is so exceptional, let's clarify what negative polarization entails. When light scatters off dust grains at small phase angles close to the line connecting the sun and the observer, the polarization can dip below zero. In simple terms, the electric field oscillations of the scattered light are oriented in a way that produces a negative value when measured. This phenomenon, known as a negative polarization branch, is not entirely foreign to astronomers. It appears in some bodies within our solar system, but typically these negative branches are shallow and broad, spreading over a wider range of phase angles. What makes Atlas extraordinary is that its negative branch plunges to about -2.7% at around 7 degrees, then inverts and crosses back into positive polarization near 17 degrees. The combination of depth and narrowness of this negative branch has no precedent. It's been observed in no comet or asteroid before, not even in 2I Borisov, the previous interstellar comet. This raises a fundamental question. Why is this so strange? To put it plainly, when sunlight scatters off dust particles near backscattering angles, the angles close to the direct line between the sun and the observer, certain optical effects come into play, such as coherent backscatter and shadow hiding. These effects can cause the polarization to dip below zero. However, the specific depth and narrowness of Atlas's negative polarization feature indicate that the dust's microstructure is unlike anything we've seen before. The properties of the dust grains, whether they are fluffy aggregates consisting of tiny monomers loosely bound together or densely packed compact particles, directly influence the shape of the polarization curve. Fluffy, loosely assembled grains tend to produce broader, shallower negative branches, while more compact, solid grains tend to yield different signatures. Factors such as porosity, surface coatings of organics or ice, and even magnetic inclusions that could influence how grains stick together in the coma all play roles in shaping this polarization signature. Given this, what could produce a deep, narrow negative polarization branch like the one observed in Atlas? Several possibilities emerge. It could be fluffy aggregates with a very specific distribution of grain sizes, or compact grains with unusual refractive indices, meaning their optical properties deviate from typical dust particles. Alternatively, the grains might have high porosity but be organized into fractal, self-similar clusters, or perhaps possess organic or icy coatings that alter their scattering behavior. Some more speculative ideas include the influence of magnetic inclusions within the grains, which might affect how they aggregate, though this remains less certain. The crucial point to recognize is that multiple combinations of physical parameters can produce similar polarization signatures. Consequently, polarization measurements alone cannot definitively determine the precise microstructure of the dust grains. Nonetheless, these observations are powerful enough to rule out certain models, most notably the standard fluffy aggregate model that adequately explains most solar system comets. When combined with other data, such as spectroscopic analysis, a clearer picture begins to emerge. For example, spectroscopic observations from the James Webb Space Telescope have detected absorption features consistent with water ice, indicating the presence of icy grains. Additionally, color measurements, extrapolated to small phase angles, suggest that Atlas's surface exhibits a reddish hue, similar to certain trans-Neptunian objects and centaurs like Phoulis. A red surface often hints at the presence of complex organics or irradiated ices, which further informs our understanding of the material makeup. Altogether, the polarization data, spectral features, and color measurements converge into a compelling, if still incomplete, narrative. The dust in Atlas's coma appears to have microstructural properties and compositional characteristics that challenge our typical expectations for interplanetary dust. These clues suggest a particle population that might have formed in a markedly different environment or undergone unique processes compared to familiar solar system objects, hinting at a fascinatingly exotic or ancient origin. The composition of Atlas's dust, rich in red-hued particles, icy grains, and exhibiting an extraordinary polarization pattern, may be revealing secrets about the environments in which such grains coagulate and grow. These clues suggest that the dust in this interstellar visitor might originate from a planetary system that experienced conditions quite unlike those familiar to us. It's a tantalizing hint that the processes of planet formation, dust accumulation and grain growth could operate differently elsewhere in the galaxy, influenced by local temperature, pressure, chemical makeup, turbulence, and other environmental factors. Such differences aren't inherently exotic. They are natural variations that physics allows when the conditions shift. Now, I want to address a speculative idea that has been circulating in recent conference discussions and online forums. An idea that warrants clarity. Some have proposed the notion of engineered microstructure, suggesting that the polarization signature we observe might not be purely natural, but in principle designed. The argument goes that if an advanced civilization aimed to create a specific scattering pattern, it could engineer dust grains with precisely tailored sizes, shapes, and compositions to produce such effects deliberately. However, I must be unequivocal. There is no peer-reviewed scientific evidence supporting this hypothesis. It remains a fringe idea, a speculative what-if story rather than a grounded scientific claim. We include it here not as a serious explanation, but as a reflection of how fascinating ATLAS is, how it pushes us to contemplate what might be possible, extending our imagination beyond the realm of likelihood into the domain of theoretical possibility. The most probable explanation, and the one supported by current evidence, is that the dust is entirely natural, albeit with properties that are unusual, yet entirely consistent with natural processes. This leads us to an exciting scientific implication. Atlas's dust may serve as a probe into different coagulation regimes that operate in other star systems. Dust growth within protoplanetary disks depends heavily on a variety of factors: temperature, pressure, chemical composition, turbulence, and more. If ATLAS originated from a system where these environmental parameters differed significantly from those of our solar system, the dust particles that formed there might possess characteristics quite unlike those we observe locally. This is not an exotic scenario. It's just physics playing out in a different sandbox, highlighting the diversity of planetary systems across the galaxy. And this is what makes the study of interstellar objects so profoundly interesting. Each one potentially offers a unique glimpse into planet formation conditions that we might otherwise never be able to investigate directly. Furthermore, the peculiar polarization pattern, specifically the deep and narrow negative polarization branch, has important implications for our physical models of scattering. When scientists attempt to match observed scattering behaviors with theoretical models, they must account for multiple factors: the contribution of single versus multiple scattering events, the complex refractive indices of dust grains, size distributions, shapes, and compositions. ATLAS's unusual polarization profile challenges these assumptions, pushing existing models to their limits. Different research teams are exploring various approaches. Some are developing fractal aggregate models with specific monomere sizes, while others are investigating coated sphere models. Each approach aims to explain the peculiar polarization features. What's clear is that ATLAS is effectively stress testing our understanding of light scattering phenomena, and the insights gained will likely refine models applicable not only to interstellar objects, but also to a broad range of solar system and exoplanetary dust studies. Looking ahead, as ATLAS approaches smaller phase angles relative to Earth, a geometric configuration that occurs as it moves closer to perihelion, we can anticipate more polarization data. Researchers will examine whether the negative polarization branch shifts or if the inversion angle evolves, which would suggest changes in dust properties. Additionally, they will look for hysteresis effects, differences between the polarization curve during inbound versus outbound trajectories. That could reveal how the dust environment transforms as the object becomes more active. High-cadence polarimetry, if achievable, could also detect temporal variability, offering clues about the spin state, jet activity, or surface heterogeneity of ATLAS. In essence, polarization measurements serve as a diagnostic tool for understanding the nature of the dust, but they also act as a window into the forces acting on Atlas itself, its engine, so to speak. Here's a point that should immediately set off warning signals within our scientific community. Atlas is exhibiting active outgassing. It is continuously releasing gas and dust into space. Despite this vigorous activity, we have yet to detect the one phenomenon we would naturally expect: a measurable change in its trajectory, an acceleration caused by the outflow. Let's examine this discrepancy, which we might term the mystery of the missing acceleration, more closely. To do so, it's instructive to revisit the case of Oumuamua, the very first confirmed interstellar visitor observed passing through our solar system back in 2017. Its passage ignited a flurry of intense debate, not primarily because of its interstellar origin, an exciting confirmation in itself, but because its observed trajectory deviated from what gravity alone could explain. Oumuamua exhibited a slight but definite acceleration, a subtle push that suggested some form of propulsion or reactive force at work. What made this particularly intriguing was that the acceleration was consistent over time and, crucially, it occurred without any detectable coma. In other words, there was no visible cloud of gas or dust, no signs of sublimating ice or outgassing, yet the object seemed to be gaining velocity in a way that implied a rocket-like effect. This sparked a variety of hypotheses. Some proposed it could be composed of low-albedo ice or exotic volatiles that sublimated without producing a detectable coma. Others floated more speculative ideas, including the possibility of an artificial origin like a light sail or an alien probe. In stark contrast, the interstellar comet Borisov, which arrived in 2019, behaved quite differently. Borisov displayed a prominent, well-defined cometary coma, a cloud of gas and dust surrounding its nucleus, just like a typical solar system comet. It also exhibited a non-gravitational acceleration consistent with the physics of gas vents pushing on the nucleus. This was textbook behavior. Gas sublimation creating jets, transferring momentum, altering the orbit in predictable ways, perfectly aligning with our understanding of cometary physics. Borisov's activity confirmed that objects from other star systems could resemble familiar comets in appearance and behavior. Now consider 3IATLAS. It shares some features with Borisov: an active coma, CO2 venting, dust production, yet perplexingly, no non-gravitational acceleration has been detected in its orbital data so far. Despite clear signs of ongoing activity, the astrometric measurements do not show the typical orbital deviations caused by outgassing. This inconsistency is profoundly strange. When outgassing occurs, the gas exerts a reactive force like a tiny thruster, pushing the object in the opposite direction of the outflow. We usually quantify this effect with parameters called A1, A2, and A3, which describe the non-gravitational forces along different axes. In the case of Atlas, these parameters remain undetected, at least in the latest orbital fits. So why might this be? Several plausible explanations come to mind. First, the geometry of the jets could be arranged in such a way that their effects cancel out when averaged over the entire object. Imagine tiny thrusters firing in all directions. If the forces are symmetrical and well-balanced, the net push would be effectively zero, resulting in no measurable acceleration. This could occur if the nucleus is tumbling chaotically, or if multiple active areas are evenly distributed, producing balanced outgassing. Second, the spin state of Atlas could be such that the jet's directions are averaged out over its rotation, diminishing any net acceleration below our detection threshold. Third, the mass of the nucleus might be sufficiently large. Hubble Space Telescope estimates place the upper limit size at about 5.6 kilometers in diameter. If Atlas is on the larger and denser end of this range, The momentum transfer from outgassing would have a correspondingly smaller effect, rendering the acceleration undetectable with current instruments. Fourth, and this is where it becomes particularly intriguing, the composition of the outgassing itself might hold clues. Observations by Webb in ultraviolet and infrared wavelengths indicate that, at approximately 3.3 astronomical units from the Sun, CO2 dominates the outgassing activity. CO2 sublimates more symmetrically than water ice because it is more volatile, meaning it sublimates at lower temperatures and does not require focused sunlight to vent. This balanced sublimation could produce a more uniform outflow, reducing the reactive force in a specific direction, and thus explaining the absence of detectable orbital acceleration. In summary, despite vivid signs of ongoing activity, the absence of the expected non-gravitational acceleration in Atlas's motion presents a compelling puzzle. It suggests that either the outgassing is geometrically arranged to cancel out net forces, or its composition and sublimation processes inherently produce a symmetric non-pushing outflow, or the object itself is simply too massive and dense for the gas vents to produce a measurable effect at this stage. As our observations continue, especially as Atlas approaches perihelion and its activity possibly intensifies or changes water, contrasting sharply with CO2, tends to produce more focused directional jets, especially when activity is concentrated in specific localized regions on a comet or interstellar object. If, in Atlas's case, the activity at its current distance from the Sun is predominantly driven by CO2 sublimation, and if that venting occurs in a relatively uniform, symmetric fashion, this could neatly explain the absence of a significant non-gravitational acceleration signal in its orbit. The true test of this hypothesis will occur as Atlas approaches perihelion. If the activity shifts, if water ice begins to sublimate and vent asymmetrically, it should induce measurable non-gravitational effects, which would manifest as identifiable A1 and A2 terms in the orbital fit calculations. Now I'd like to entertain a speculative idea here, clearly marked as a narrative device rather than a scientific assertion. In science fiction, the concept of inertial damping is often invoked as a mechanism that suppresses or counteracts acceleration, thereby maintaining an object's stability against the chaos of cometary outgassing or other forces. Could Atlas, with its dense insulated surface and symmetric CO2 venting, somehow mimic such a control mechanism? Might it give the impression of a stable, controlled object, almost as if it's resisting the typical turbulence and unpredictability we associate with natural comets? The answer almost certainly is no. All current understanding of natural processes provides a perfectly adequate explanation for what we're observing. Yet the very fact that this question can be posed, that Atlas's seemingly unusual behavior sparks curiosity and wonder, says something important. It highlights how extraordinary it is that we are even contemplating these possibilities, and it underscores the significance of what we might observe at perihelion. What should we particularly be on the lookout for? If, as Atlas approaches the Sun, water ice begins to sublimate and the jets become visibly asymmetrical, we would expect to see non-gravitational terms emerge clearly in the orbit determination data. Should these terms align with the typical patterns of cometary outgassing, then the mystery would quickly resolve itself, confirming Atlas as a natural, albeit unusual, comet. However, if despite increased activity no measurable non-gravitational acceleration appears, if Atlas continues to exhibit signs of activity without any detectable change in its trajectory, then we move into truly puzzling territory. Such a scenario would suggest something unusual about the object's nuclear structure or spin state, perhaps a very specific configuration that cancels out the forces we usually associate with outgassing, or some other mechanism we don't yet understand. This question isn't merely academic. It has practical implications for future exploration. If Atlas's trajectory remains predictable, undisturbed by large non-gravitational perturbations, then planning interception or sample return missions becomes significantly simpler. Knowing where the object will be years in advance is crucial for mission design. Unpredictable comets are poor candidates for close-up studies or rendezvous. Conversely, stable, predictable interstellar visitors are prime targets for in-depth exploration, maybe even future flybys or sample return endeavors. Beyond its chemical, optical, and dynamical peculiarities, Atlas introduces yet another layer of intrigue, one that touches the realm of coincidence and celestial geometry. When we map back its origin point on the sky, considering the direction from which it approached before the sun's gravity bent its path, something about the geometry makes many observers uneasy. Not necessarily scientists. Scientists are well versed in understanding the effects of observational biases, selection effects, and statistical distributions. But for the public, the bloggers, the curious minds who see patterns and ask if they hold deeper meaning, these features can evoke suspicion or awe. This leads us to the concept of the geometry of coincidence. Every interstellar object has a radiant, a specific point on the celestial sphere from which it appears to originate, prior to the gravitational influence of the sun altering its trajectory. Think of this radiant as a reverse vanishing point. If you could stand outside our solar system and observe Atlas approaching, you'd see it seemingly coming from a particular region in space projected onto the sky. This geometric point, the radiant, serves as a celestial fingerprint hinting at the object's initial direction of travel through the galaxy. Imagine yourself standing beyond the boundaries of our solar system, gazing outward as Atlas makes its approach through the vast cosmic expanse. From this vantage point, you'd observe it coming from a specific point in space, a precise direction that, when projected onto the celestial sphere, is known as the radiant. For the interstellar visitor designated as 3I, or simply Atlas, this radiant lies within a defined region relative to the galactic plane and the sun's motion through the galaxy's local standard of rest. This motion of the sun, as it journeys through its neighborhood in the Milky Way, sets a reference frame, the local standard of rest. The models that scientists employ to understand such objects provide predictions about where and how these interstellar visitors should appear. One prominent framework is the Oxford model, a comprehensive synthesis that considers how planetary systems eject objects into interstellar space. According to this model, we expect to observe interstellar objects with a broad spectrum of speeds and directions, what astronomers call radiants. Most of these objects originate from stars similar to our Sun, stars nestled within the galactic disk, which orbit the galaxy's core in a relatively flat and orderly fashion. But the ejection process from planetary systems isn't a gentle affair. It's inherently chaotic. Gravitational interactions, close encounters with other stars, and the scattering of planets and debris can propel objects at high velocities. This chaotic scattering introduces a high-velocity tail in the distribution, meaning some objects are flung outward at speeds much faster than the typical ejection velocities. In the case of Atlas, its measured speed, about 58 kilometers per second relative to the Sun, and its radiant direction align well within the expected range of these ejected interstellar objects stemming from the galactic disk. It isn't an anomaly or outlier in the context of the model. Rather, it fits comfortably within the predicted spectrum, though it remains somewhat unusual among the known objects. Further validation comes from kinematic diagnostics developed by astronomer Perez Couto. These analyses suggest that Atlas's motion is consistent with a thin disk star, meaning it's part of the galaxy's younger, relatively flat component, despite its notably large peculiar velocity. Now, the term peculiar velocity may sound exotic or suspicious, implying that the object might be doing something atypical or unnatural. but in reality it's a technical phrase. It refers simply to the object's velocity relative to the local standard of rest, the average motion of stars in the neighborhood. Stars, especially the older ones, can have significant peculiar velocities because they've been gravitationally stirred and perturbed over billions of years. This process is akin to a boat drifting through turbulent waters. The more turbulence, the more erratic the trajectory. Atlas's motion, with its large, peculiar velocity, is entirely consistent with this history. It's not a member of the galaxy's halo or an interloper from a different population. It belongs to the disk, just like many stars, but with a history of gravitational stirring that has given it a more energetic and unusual orbit. Now, why do so many observers and online commentators focus on apparent alignments or coincidences, such as the suggestion that Atlas's approach direction is precisely aligned with the solar apex, or that it passed surprisingly close to Mars within about 29 to 30 million kilometers? The reason is rooted in our innate pattern-seeking nature. Humans are naturally inclined to find meaning in patterns and correlations. When Atlas approaches from a certain direction and passes near planetary orbits, it's tempting to see deliberate design or significant coincidence. But here's the crucial point. Maps of the sky, especially when projected onto 2 dimensions, are inherently deceptive. They don't perfectly represent 3-dimensional space. When you flatten a 3-dimensional volume onto a 2-dimensional chart, objects that are actually far apart in space can appear close together. This is a process called projection, and it inevitably introduces distortions. Furthermore, our telescopic surveys don't scan the entire sky uniformly. They focus on specific regions, areas where they have the best chance of finding near-Earth objects or other targets of interest. These footprints of survey coverage mean that some directions are observed more intensively than others. As a result, if an object like Atlas is detected coming from a region that has been heavily surveyed, it may seem to align with certain features or patterns. But this apparent alignment is often a product of the survey's biases rather than any underlying cosmic coincidence. In fact, the distribution of detected objects is heavily influenced by the coverage patterns of the telescopes and surveys we use. For example, the survey pattern optimized for finding near-Earth asteroids, such as the one that discovered Atlas, has a particular focus on certain parts of the sky. If Atlas's radiant falls within those regions, it increases the likelihood of detection, not because it's special or targeted, but simply because we're looking there more often. In short, humans tend to interpret these alignments and passings as meaningful, but in reality they can be illusions. The fact that Atlas appears to be in a certain region of the sky does not necessarily mean that interstellar objects are clustering there. Instead, it indicates that our searches and observations are inherently clustered in those areas. Galactic substructure, such as moving groups, stellar streams, and regions of recent star formation, adds another layer of complexity. These features create regions of higher or lower star density, leading to non-uniform distributions of potential parent stars for interstellar objects. If Atlas originated from a part of the galaxy that is sparsely sampled by our surveys, perhaps an underpopulated or faint region, it might seem isolated in our data, even if its true origin lies elsewhere. This is a natural outcome of the biases built into our observational models. When scientists simulate populations of interstellar objects, ISOs, and incorporate the biases of current surveys, such as sky coverage, detection thresholds, and measurement limitations, they often produce what are called empty cone patterns. These are regions in the sky where models predict we should expect to find interstellar objects, but where we never observe a parent star. The absence of a detectable star in those regions doesn't necessarily mean the parent star isn't there. Rather, it may be too faint to observe with current instruments, lack a measurable radial velocity, or simply sit outside the volume of our surveys. If Atlas is sitting in such an empty cone, then the mystery of its origin isn't rooted in cosmic anomalies or alien engineering, but rather in the limitations of our observational reach. In other words, the true source could be lurking just beyond our current detection capabilities, hiding in the shadows of our incomplete sky maps. Now, shifting to a point that has been circulating widely in public discussions. The idea that Atlas is close past near Mars, its alignment with planetary orbits, or crossing the ecliptic plane are extraordinary coincidences. These are, in fact, grounded in the realities of orbital mechanics. Any interstellar object entering the inner solar system on a hyperbolic trajectory must cross the ecliptic plane at some point because that's the plane in which most planets orbit the Sun. Since the planets are predominantly arranged along this plane, crossing near a planet like Mars is not unusual. It's almost inevitable. The misconception often arises in the misinterpretation of probability calculations. Many of these calculations focus narrowly on the chances that a specific object's trajectory would pass close to Mars on a particular date. Such a probability is indeed very low because it involves precise alignments in space and time. However, this is a limited perspective that changes when we broaden the question. What are the odds that any interstellar object we discover will pass within some distance of some planet at any time? When phrased that way, the numbers grow considerably because the search space expands dramatically. Imagine, for example, a sky map overlaid with the predicted density of incoming interstellar objects, their radiant regions where most are expected to originate. Darker areas of this map are regions with higher predicted arrival densities, while lighter regions are less likely. Atlas's inbound trajectory points from a region that is neither the densest nor the sparsest, but somewhere in the middle. When we overlay the coverage of our surveys, those regions we examine most intensely, it becomes clear that we are more likely to have found Atlas simply because we were looking in a direction where objects like it could be detected, not because Atlas was specifically targeted or intentionally aligned with us. Regarding the alignment with the solar apex, the direction in which the Sun moves through the galaxy at about 240 kilometers per second toward the constellation Hercules. Atlas's velocity vector has some component aligned with this motion. This, however, is not evidence of deliberate targeting or alien intervention. Instead, it reflects the natural distribution of velocities among ejected objects originating from the galactic disk. Stars and objects expelled from their birthplaces tend to have velocity components that mirror the overall rotation of the galaxy. Some are aligned with the Sun's motion, others are not. Atlas's somewhat aligned trajectory simply falls within the expected range of natural ejection scenarios, and it does not suggest any purposeful targeting or extraordinary coincidence. When we consider Atlas as originating from the galactic disk, I want to clarify a crucial point. The seemingly coincidental alignments, such as its close approach to Mars, the timing of its entry, and the direction from which its radiance appears, are not random or meaningless. These details are genuinely intriguing. They add a layer of narrative richness and make the story more compelling. However, it's important to distinguish between what is interesting and what is truly anomalous. Just because these occurrences seem noteworthy doesn't mean they defy natural explanation. The antidote to the anxiety caused by coincidence, what some call coincidence bias, is better statistics and a larger sample size. In the future, as we observe more interstellar visitors, say, reaching a total of 10, we will have enough data to analyze how many of these objects pass near planets, how often their radiance align with certain regions of the sky, and whether these patterns are statistically significant. Once our sample grows to 100 or more, we can begin constructing a meaningful map of the distribution of their radiance in the sky, revealing underlying patterns or biases in their origins or detection. Currently, with only 3 interstellar objects observed, we are still in the realm of anecdote rather than robust statistics. What can future observations tell us after perihelion? First, a more refined measurement of Atlas's radiant will sharpen our understanding of its original incoming direction. Second, improved estimates of its inbound velocity vector will tighten the constraints on where it might have come from in the sky and how fast it was moving before the sun's gravity captured it. If the radiant position shifts significantly with better data, some of the apparent alignments or patterns will likely dissolve, reducing the impression of coincidence. Conversely, if the radiant remains roughly consistent, we will have a much more precise target for future efforts to trace its origin when more comprehensive stellar catalogs become available. But velocity, its magnitude and direction, doesn't tell the whole story. It's not just about where Atlas came from. It's also about how fast it was moving relative to the local standard of rest, or LSR, a frame of reference representing the average motion of stars in our neighborhood. Atlas's velocity is notably high, not impossibly high, but sufficiently fast to raise eyebrows. This is because within the galactic velocity field there are recognizable patterns. Young stars tend to drift slowly relative to the LSR, while older stars have had more time to be gravitationally perturbed and thus move faster. The velocity of an interstellar object encodes its dynamical age, the amount of time it has spent being scattered or kicked around by gravitational interactions. If we treat Atlas's speed quite seriously, then calculating how long it would take to accumulate such velocity through known natural processes yields an unsettling conclusion. Atlas may be older than many initially suspected. This brings us to what I will call the forbidden speed window. Atlas's inbound velocity relative to the Sun is about 58 kilometers per second, with an orbital eccentricity of roughly 6.1. This eccentricity signifies a deeply hyperbolic trajectory, unmistakably interstellar and not marginally unbound like some long-period comets that drift inward from the distant Oort cloud. Such a hyperbolic orbit leaves no doubt about its interstellar origin. Now, 58 kilometers per second, while rapid compared to typical long-period comets, which usually enter the inner solar system at speeds between 10 and 30 kilometers per second, is well within the predicted range for interstellar objects ejected from other star systems. Some population models even suggest that interstellar objects can be traveling up to 70 or 80 kilometers per second when they encounter our solar system. Therefore, Atlas's velocity, though high, is not outside the realm of expectation for such objects. The complication arises when we begin to consider its age. Kinematic age dating, an approach that estimates how long an object has been traveling at its current velocity, has been attempted. Researchers such as Hopkins and Taylor, along with Seligman, have analyzed Atlas's velocity distribution to infer its age. Their estimates span from roughly 3 billion to 11 billion years, depending on the underlying assumptions and prior models used. A separate study suggests a lower bound exceeding about 7.6 billion years. These figures are striking because they surpass the age of our solar system. The Sun, after all, is about 4.6 billion years old, and Earth is approximately 4.5 billion years old. If Atlas is indeed older than 7 billion years, then it was wandering the galaxy long before our solar system even formed. Perhaps when the galaxy was still young, in an era when the first generations of planetary systems were just beginning to coalesce around ancient low metallicity stars. This realization is profound. It suggests that Atlas could be an ancient traveler, predating the Sun and perhaps originating from a primordial epoch of galactic history. Such a perspective challenges our notions of typical interstellar objects as relatively recent visitors. Instead, it opens the possibility that some— let me distill this reasoning into straightforward terms. The concept of the local standard of rest, or LSR, is essentially the average velocity of stars in our immediate cosmic vicinity. It acts as a benchmark, representing the collective motion of the galactic disk. Think of it as a baseline speed that most stars roughly share. When stars form from well-mixed interstellar gas, they tend to move close to this average because they inherit the motion of their birth material. These young stars haven't yet experienced significant gravitational nudges that could alter their paths. As stars age, however, they orbit the galaxy repeatedly, sometimes dozens, sometimes hundreds of times, passing through various regions filled with other stars, gas clouds, and dynamic structures like spiral arms. Each encounter or gravitational interaction imparts a small velocity change, what we call a kick. Over vast cosmic timescales, these incremental nudges accumulate, causing a star's motion to drift away from the original galactic baseline. This drift is what we refer to as the star's peculiar velocity, and it functions like a kind of cosmic clock. The larger the offset from the standard motion, the more likely the star has been around for a longer period. Applying this to Atlas, its observed motion reveals a significant offset from the local standard of rest, which hints at an advanced age, perhaps several billion years. Yet there's a subtlety here. The relationship between a star's velocity dispersion, the spread of velocities within a population, and its age isn't a simple one-to-one correlation. It's inherently probabilistic. For instance, a relatively young object could have received a substantial velocity kick early on, making it appear older than it truly is. Conversely, an ancient star might have avoided major disturbances, maintaining a velocity close to the baseline and therefore look deceptively young. Hence, when someone estimates Atlas to be around 7 billion years old based on its velocity, they're not stating a precise age, but rather providing a probabilistic inference grounded in statistical averages from stellar populations. Even with this nuance, the numbers tend to point toward an old age for Atlas. Now, why does the idea of a forbidden window in velocity space come into play? Well, many assume that interstellar objects should have velocity distributions similar to nearby stars, which often approximate a Gaussian spread centered around the galactic standard. But reality is messier. Stellar velocities aren't perfectly Gaussian. They are structured and clumped into subgroups like moving groups, stellar streams, and associations. These groups can have their own characteristic bulk motions, meaning that an object originating from such a group might have a velocity that doesn't neatly fit the average distribution. Therefore, the notion that Atlas's high velocity is too anomalous to be explained by natural galactic processes collapses once we recognize this substructure. The forbidden window, the idea that its speed is outside the realm of what natural mechanisms could produce, loses its footing when we understand the complex, non-uniform nature of stellar velocities in the galaxy. So what natural processes could have gradually altered Atlas's speed over billions of years? First, stellar flybys. Each pass within a few parsecs of a star would exert a tiny gravitational tug, and although each individual tug is negligible, their cumulative effect over cosmic timescales can be significant. Second, dense gas clouds in the galaxy can act like gravitational slingshots or exert drag, depending on the relative motion and geometry involved. Third, the galaxy's gravitational potential itself isn't uniform. As Atlas orbits through different regions, spiral arms, the galactic halo, or the dense core, it can gain or lose energy. Spiral arm crossings in particular can perturb orbits through gravitational density waves, nudging objects in various directions. All these are well understood natural processes capable of gradually accelerating or decelerating objects over billions of years. potentially pushing their velocities into the tens of kilometers per second relative to the galactic standard. Now I'll introduce some speculative ideas, what I'll call imaginative notions, clearly labeled as such, not claims. For example, could the interstellar medium's magnetic field subtly slow down a charged object over eons? In principle, yes, but the effect would be minuscule unless the object traversed regions of exceptionally dense, strongly magnetized plasma. Similarly, some fringe theories entertain the possibility that exotic physics, such as interactions with dark matter or modifications to gravity, could influence an object's velocity without the need for stellar encounters. And even more speculative, some have wondered if a civilization might have engineered a propulsion or deceleration mechanism that has been gently adjusting Atlas's speed over billions of years, though there's no evidence to support such a hypothesis. These ideas remain purely in the realm of imagination, not established science. In essence, the core takeaway is that natural mechanisms, stellar flybys, gas clouds, galactic tides, spiral arm effects, are all capable of gradually shaping the velocity of interstellar objects like Atlas over immense timescales. The observed could the interaction with a non-Newtonian gravitational medium, some form of exotic dark matter, or even a modified theory of gravity itself influence an object's velocity without the need for close stellar encounters? This idea delves into fringe physics, well beyond the scope of current observational evidence, yet it persists as an intriguing hypothesis occasionally discussed in specialized circles. One plausible, albeit speculative, scenario is the possibility of an advanced artificial propulsion system. Imagine a device that has been intermittently firing over billions of years, gradually adjusting an object's trajectory and explaining its seemingly fine-tuned anomalous velocity. Such a mechanism might mimic the effects of natural forces but operate through processes we have yet to understand or detect. Again, this remains purely in the realm of conjecture, with no empirical support at present. Nonetheless, it forms part of the discourse surrounding these mysterious objects. So how might we go about testing these highly unconventional ideas of exotic braking or non-standard deceleration? One promising approach is to examine the object's spin state and rotational evolution. If Atlas has been subjected to external influences beyond the typical outgassing and sublimation processes we associate with comets, perhaps some form of external torque, its rotation might reveal anomalies. For example, irregularities in its spin period, precession, or tumbling motion could hint at forces beyond what standard physics would predict. Additionally, analyzing the asymmetry of its jet activity provides another avenue. If the jets, streams of outgassing material, are firing in a manner that acts to dampen the object's orbital variations rather than amplify them, such behavior should be measurable. Variations in velocities before and after perihelion, so-called pre-perihelion versus post-perihelion velocity shifts, that cannot be accounted for solely by gravitational interactions or typical cometary outgassing would serve as red flags pointing toward more exotic influences. As of now, no such anomalies have been detected in Atlas. Its behavior remains consistent with natural expectations, and the idea of exotic physical mechanisms acting as a form of brake or deceleration is at this point a solution searching for a problem. Now, bridging into the next aspect of this enigma, consider the profound relationship between an object's velocity and its age, particularly when that velocity is unusually high. If Atlas has been wandering the galaxy for billions of years, the sheer number of stars it has passed and the gravitational interactions it has experienced would be astronomical. Each encounter, no matter how slight, introduces a bit of noise into its orbital history. Over time, these countless small perturbations accumulate, making the orbital path increasingly chaotic and uncertain. By the time we attempt to trace the object's history back 10 million years through models and simulations, The original trajectory is no longer discernible. Instead of a precise path, we find ourselves with an ever-expanding cloud of possible trajectories. The original timeline, its true past, does not simply fade into obscurity. It effectively vanishes into chaos. Imagine trying to reconstruct the journey of a single pebble in a riverbed after flowing for 10 million years. The pebble still exists, and you could hold it in your hand today. But the specific route it took, its upstream path, has been washed away by trillions of turbulent eddies, each subtly nudging it in different directions. The physics governing the flow are reversible in principle. Newton's laws work both forward and backward. But the essential information needed to reverse the pebble's precise trajectory, such as the position and velocity of every water molecule at every moment, has dissipated into entropy. In the case of Atlas, the Milky Way acts as the river, and the passage of 10 million years is the long, turbulent flow that erodes the clarity of the orbital record. The research team led by Pericuto chose to halt their orbital traceback at this point precisely because beyond 10 million years, meaningful reconstructions cease. The reasons are twofold. First, the chaotic nature of stellar and interstellar object orbits means that minuscule uncertainties in initial conditions grow exponentially over time. Small errors in initial velocity, position, or assumptions about the galactic potential cause the set of possible past trajectories to spread out into an enormous, indistinguishable cloud, so large that individual paths lose their meaning. Instead of tracking a unique history, what remains is a scattering of possibilities akin to merely calculating noise rather than history. Second, limitations in our current catalogs impose fundamental constraints. The Gaia mission, which provides the most precise stellar data to date, offers radial velocities for only the brightest stars within a few hundred parsecs. Beyond that distance, the data becomes sparse or absent. Consequently, any attempt to retrace a path involving stars or regions beyond these limits is inherently incomplete, leaving gaps that prevent definitive conclusions about Atlas's origin. In essence, after roughly 10 million years of backward integration, the combined effects of chaos and observational limits render the pursuit of a precise, meaningful orbital history impossible. The universe, in its vast complexity, has effectively erased the detailed record of Gaia, has provided us with radial velocity data for only a subset of stars, primarily the brighter ones located within a few hundred parsecs of Earth. Once you venture beyond approximately 500 parsecs, the completeness of these measurements plummets dramatically, creating a steep drop-off in available data. In practical terms, this means that even if Atlas originated from a star situated 2,000 parsecs away, our current data set would lack the necessary information to test or confirm that connection. The combined limits of our observational capabilities and the chaotic nature of stellar and interstellar dynamics converge around the 10 million year mark, signaling a natural boundary where further attempts become futile. Both factors, instrumental limitations and the inherent unpredictability of gravitational interactions, advise us to cease trying to trace the object's origins beyond this time frame. This phenomenon, where the universe forgets its own history, is not a failure of physics. Rather, it is an intrinsic feature of information theory. The universe does not maintain a comprehensive ledger of every trajectory taken by each object. Instead, information about past states is continually being thermalized, mixed into the cosmic fabric, and ultimately lost to entropy. While the past of any object, its origins and the chain of events that led to its current state, exists in a physical sense, retrieving that history is not guaranteed. In principle, the causal chain that links Atlas back to its birthplace remains intact. Nonetheless, after sufficient interactions over vast spans of time, the information necessary to reconstruct that chain becomes so scrambled that it is effectively unrecoverable in practice. Atlas's past, therefore, is something that once existed, somewhere in the universe. But the universe's bookkeeping system has long since shredded the receipt. This realization matters far beyond the specific case of interstellar object 3I. We are on the cusp of entering an era characterized by frequent discoveries of such objects. The forthcoming Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, LSST, is poised to revolutionize our observational reach. By surveying the entire southern sky every few nights with unprecedented depth, Rubin will be capable of detecting faint, distant objects that previously escaped notice. Estimates suggest that once fully operational, the observatory could identify dozens to hundreds of interstellar visitors every year. Most of these will resemble 3I, ancient, with untraceable origins due to the cosmic amnesia we've discussed. However, among these, a fortunate few will be objects that have been recently ejected from their parent stars, perhaps within the last few 100,000 to 1,000,000 years, meaning their orbital histories remain accessible and their origins still within our reach. What would it take to trace Atlas's origins if future data improve? First and foremost, we would need more precise stellar radial velocities, especially for the faint stars that Gaia currently cannot measure effectively. Although Gaia's future releases will extend the depth of its measurements, there are fundamental physical and technological limits to how faint an object we can analyze for radial velocity from ground or space-based observatories. Hypothetically, missions designed to map stars down to the 10th magnitude or fainter, providing complete six-dimensional data, positions, proper motions, parallaxes, and radial velocities, would significantly expand our reach. Additionally, understanding the density and velocity structure of the interstellar medium along Atlas's past trajectory would be invaluable. If we knew how gas and dust were distributed and moving through those regions, we could incorporate drag and perturbative effects into our models, creating a more accurate reconstruction of its path. But such detailed interstellar media mapping remains a goal for the future. Currently, it exists only in the realm of aspiration. Right now, however, Atlas's timeline, the sequence of its past encounters and origins, has faded into a fog of uncertainty. There is a fundamental philosophical point to consider here. The existence of physical causes is undeniable. Atlas was ejected from a planetary system, and that ejection event was driven by an identifiable cause. The star responsible for that ejection still exists, or at least did at some point, and the gravitational interactions that molded Atlas's journey over billions of years undeniably occurred. None of this is in doubt, yet the ability to reconstruct this chain of causality from our current observations can break down. This is not because the causes did not happen, but because the information about those causes has been scrambled and dispersed beyond our capacity to recover it. It is akin to asking what the weather was on a specific day 3 billion years ago. The weather indeed happened, driven by complex atmospheric and planetary processes. However, the detailed data, records of temperature, pressure, cloud cover, and wind patterns are no longer available. The information has been dissipated into the chaos of the planet's atmosphere and the passage of geological time. In the case of Atlas, its past exists in principle. It was ejected from a star, from a planetary system, through a sequence of gravitational encounters. Those events shaped its journey, yet in practice, the universe's own entropy and the limitations of our data mean we can no longer trace that journey. The origin of Atlas, much like a message lost in the vastness of the universe, has faded into the indistinct background noise that pervades the atmosphere, oceans, and crust of our planet. Dissolved into the thermal hum that masks every faint whisper of its past. It's not that the information has been deliberately erased, rather it has been irretrievably mixed, scattered beyond retrieval. The same principle applies to Atlas's origins. while the direct dynamical trail, tracing its path back through the gravitational dance of stars, has vanished into the cosmic ether, we are not entirely left in the dark. Instead, we turn to chemistry as our surrogate guide. Its composition, the overwhelming presence of carbon dioxide, the polarization signature it exhibits, and the dust's physical properties, serves as environmental clues, subtle breadcrumbs that hint at the neighborhood from which it once came. These clues don't pinpoint the exact address of the parent star, but they do sketch out the kind of galactic environment Atlas inhabited. Cold, rich in carbon compounds, possibly ancient, and shaped by processes long past. In the absence of a clear orbital genealogy and detailed map of its stellar ancestry, these chemical signatures become our breadcrumbs, illuminating the story of its origin in a landscape we cannot directly reconstruct. Allow me to extend this line of thought into the realm of pure speculation, clearly marked as such. Suppose Atlas is truly a relic from the distant past, an entity that has been wandering the galaxy for perhaps 7 or even 10 billion years. Such an age would mean it predates many significant events in galactic history. For instance, the Gaia and Hubble collision, a colossal merger event that occurred roughly 10 billion years ago and introduced a dwarf galaxy into the Milky Way, dramatically stirred the galactic disk, catalyzed star formation, and altered the chemical fabric of our galaxy. If Atlas predates this event, then it must have formed during a time when the galaxy's environment was fundamentally different, when the Milky Way was still in its formative stages with a chemical makeup now lost to the annals of cosmic evolution. Its chemistry, therefore, could reflect a galaxy that no longer exists in its original form, a primordial environment with conditions and compositions that are long gone. While such a hypothesis seems like a long shot, it remains tantalizingly plausible, hinting at a history buried deep in galactic antiquity. Earlier I mentioned that certain studies, like those analyzing gases from interstellar objects, have identified many close stellar passages in their attempts to trace Atlas's past. These results, however, don't align neatly with the reconstructions from other teams, such as Periscuto's. Why? The answer lies in the differences, initial assumptions, the uncertainties inherent in orbital calculations, the particular stellar samples chosen, and the integration methods employed. When these methodologies are reconciled, the apparent discrepancies begin to make sense. Yet regardless of which study one considers or which data set is trusted, the fundamental conclusion remains unwavering. No definitive parent star or stellar system has been identified. There have been numerous close encounters with stars along the possible trajectories, but none that are sufficiently nearby, slow-moving, or gravitationally influential to explain Atlas's current path. The timeline in this context has become scrambled for everyone involved, an inscrutable jumble of possibilities where the original origin has been effectively erased. This leads us to a sobering reality. Orbital traceback, our primary tool for unraveling origins, has become a dead end. Despite the immense power of our most advanced telescopes, Hubble, Webb, and a host of ground-based instruments, we find ourselves met with a curious silence, a conspicuous absence of certain critical data we would have expected to gather by now. Part of this silence stems from the fundamental laws of physics, part from logistical limitations. In the gaps, speculation begins to flourish. Let us consider the so-called silence of the sensors. Hubble, for example, has provided an upper limit on Atlas's nucleus size, roughly 5.6 kilometers, based on the amount of light it can detect that isn't attributable to the coma. This isn't a direct image of the nucleus. Rather, it's a limit constrained by our instrument's sensitivity. The nucleus itself is concealed beneath the luminous glow of gas and dust, making direct imaging impossible at this stage. To determine its size with certainty, we would need to model the coma, subtract its contribution from the observed light, and analyze what remains. Depending on assumptions about albedo and activity, the residual could correspond to a physical body ranging from a few hundred meters to several kilometers across. But crucially, we have no radar data from ATLAS. There have been no radar echoes, no reflections acquired from the object, and that absence is telling. Why is this significant? Because radar offers a different avenue of insight. It can directly probe the size, shape, and surface properties of small bodies in space. Yet, despite numerous attempts by observatories including Arecibo before radar, observations of small celestial bodies rely heavily on proximity. The target must be sufficiently nearby, and its radar cross-section, the measure of how much radar energy it reflects, needs to be large enough for detection. Unfortunately, ATLAS has remained too distant for current radar systems to effectively determine its size or shape through this method. The now defunct Arecibo Observatory, which could have potentially performed such measurements, collapsed in 2020. Efforts by facilities like the Goldstone Deep Space Communications Complex and the Green Bank Telescope have been made to observe other objects. But ATLAS's current position and the geometric configuration of its orbit make radar ranging impractical at this time. This situation is purely a matter of physics and logistical limitations. There's no conspiracy behind it, just the constraints imposed by our current technology and the laws of motion. Moving beyond radar, thermal infrared data offers another avenue for understanding ATLAS's properties, but it presents its own challenges. The James Webb Space Telescope's near-infrared spectrograph has provided spectral features indicative of gas, ice, and dust, valuable clues about its composition. However, deriving a precise measurement of the solid nucleus's thermal inertia, the ability of the surface to conduct and store heat, requires isolating the thermal emission of the nucleus from the overwhelming signals coming from the surrounding coma. This coma, composed of sublimating ices and dust, scatters sunlight and emits its own thermal radiation, especially when active, making it difficult to distinguish the nucleus's intrinsic thermal characteristics. As a consequence, interpretations about whether the nucleus possesses a thick crust, a porous internal structure, or some more exotic internal makeup are premature. We simply lack the definitive data to draw firm conclusions. Furthermore, some ground-based photometric observations have reported irregularities in brightness over time, tiny fluctuations that could, in principle, hint at rotation states or surface features. But these signals are complicated because the nucleus is heavily veiled by its coma. What we see is not the bare rock itself, but a combination of rock, gas, and dust, all varying in brightness and distribution. Disentangling the rotation period, the shape of the nucleus, and the activity level based solely on pre-perihelion photometry proves extremely difficult. Different research teams are working on this problem, but their findings remain preliminary. Claims of unusual rotation states or complex tumbling motions are, at this stage, speculative. It's also crucial to emphasize that despite the visible activity, no non-gravitational acceleration, small deviations in the orbit caused by reactive forces from sublimating ices, has yet been detected in ATLAS. This is a notably clean and unremarkable result in the sense that the orbit appears to be governed solely by gravitational influences. Typically, active comets exhibit measurable non-gravitational acceleration due to outgassing, which acts like a tiny rocket thruster. The absence of such acceleration in ATLAS's orbit is unusual but can be explained by plausible scenarios: symmetric venting of gases, the dominance of carbon dioxide instead of water, specific spin geometries, or other factors. Importantly, this lack of detectable non-gravitational forces does not imply that ATLAS is artificially stabilized or that it involves exotic physics. It's simply an intriguing data point that might become clearer as we gather more precise astrometric measurements. Turning to the communication between media headlines and scientific publications, there's a notable disparity. Headlines often feature sensational images of what are described as Manhattan-sized objects, with dramatic visualizations of a Mars flyby, images that serve to capture public attention and imagination. These are useful for engagement but do not substitute for the careful, measured reports issued by organizations like NASA, the Hubble Space Telescope, or the James Webb Space Telescope. Official scientific releases acknowledge that the nucleus size remains uncertain, that the coma is rich in carbon dioxide, and that the polarization data is unusual. These statements represent the current understanding based on rigorous analysis, contrasting sharply with the often sensationalized headlines. The flyby of Atlas occurred on the night of September 29th to the 30th, 2025. During this close approach, Atlas came within approximately 29 to 30 million kilometers, roughly 18 million miles, from Earth. While this distance is significant, far too far for a skimming atmospheric-level encounter, it provided an excellent geometry for observation by orbiting spacecraft and ground-based assets. Multiple instruments, including Mars Express, NASA's MAVEN orbiter, and various surface rovers equipped with cameras, had the opportunity to observe Atlas from vantage points different from those available from Earth. This multi-perspective approach enhances our understanding by allowing detailed triangulation and more comprehensive data collection, even if the event itself wasn't dramatic in visual terms. When considering the observations made during Atlas's recent pass, particularly the multiple vantage points provided by different observatories, the value of such a campaign becomes clear. Multiple baselines allow astronomers to precisely triangulate the structure of the coma, leading to more accurate constraints on the directions from which outgassing occurs. This, in turn, can even reveal faint features and subtle asymmetries that would be impossible to detect from a single line of sight, such as from Earth alone. Even if the encounter with Mars didn't produce dramatic visuals or cinematic spectacles from a scientific standpoint, it was a treasure trove of data, offering a wealth of insights into the behavior and properties of this interstellar visitor. However, I feel compelled to address a persistent rumor circulating online, specifically claims that certain spectra or data have been deliberately withheld or suppressed because they are too anomalous or too strange to be shared with the public. Let me clarify with absolute certainty. Large-scale observational programs involving major telescopes operate through well-established, rigorous workflows. Raw data, images, spectra, measurements are processed through carefully designed pipelines that convert unrefined inputs into calibrated, scientifically meaningful results. This process takes time, sometimes months, and involves peer review, quality checks, and validation steps. The delay between observation and publication is a standard part of scientific rigor, not a sign of conspiracy or concealment. Furthermore, these pipelines and workflows are designed to ensure data quality and reliability, not to hide information. The absence of a detailed spectrum or a specific plot on the very first day of data release is entirely consistent with the normal rhythm of scientific research. If one desires real-time access to data, advocating for open policies and pipeline automation is the way forward. But it's essential to distinguish logistical delays from intentional suppression. Confusing the two only fuels misinformation. Looking ahead, what should we be attentive to in subsequent data releases? Several key indicators could shed more light on the evolving nature of Atlas. For instance, the gas ratios near perihelion will be particularly revealing. Will carbon dioxide remain the dominant volatile? Or will water begin to take precedence as the object warms? Post-perihelion estimates of the nucleus size are also significant. As the coma becomes clearer and easier to subtract from the overall image, we may be able to refine our understanding of the solid body's true dimensions. Additionally, the appearance of non-gravitational acceleration terms, parameters like A1 and A2 in orbit fits after perihelion would suggest that water jets are actively contributing to its motion, aligning with the expected behavior of sublimating volatiles. High signal-to-noise spectroscopy could offer even more detailed insights. Should someone obtain a truly pristine spectrum, it might reveal trace species, such as deuterium to hydrogen ratios, different carbon isotopes, or sulfur compounds, that serve as fingerprints of the object's formation environment. These details could unlock clues about where and how it originated, providing context that goes beyond mere dynamics. The truth is, our instruments are not being hidden or being silenced. They are simply operating at the limits of current technology and the inherent difficulty of measuring faint signals from distant small objects. The process is slow, but that's honest science, not secrecy. Now, shifting focus, I want to touch on an elephant in the room, what's often called the culture war within astronomy and the broader scientific community. This isn't just about data or observations, it's about interpretation, media portrayal, and the very question of what it means to classify something as artificial. On one side, the mainstream scientific community, researchers, refereed journals, observatory teams, generally regard ATLAS as a natural interstellar comet with some unusual traits. Its high-velocity chemical composition and polarization signatures all fall within the realm of astrophysical phenomena that we can understand through current models and theories. But there's a vocal minority, notably led by figures like Avi Loeb at Harvard, who propose the possibility that ATLAS might be a techno-artifact, an object intentionally or unintentionally engineered, perhaps by an extraterrestrial civilization. Loeb and collaborators present their hypotheses not as definitive claims, but as intriguing possibilities worth exploring. This framing has generated a certain rift within the community. Some see it as a valuable line of scientific inquiry, an honest acknowledgement that extraordinary phenomena deserve open-minded investigation, while others view it as a distraction or a form of sensationalism that risks undermining the credibility of genuine scientific research. This divergence reflects a deeper debate about how science is conducted and communicated. Should we remain cautious, sticking to well-established physics and cautious interpretations? Or should we entertain bold hypotheses, even if they challenge conventional wisdom, to ensure we're not missing something revolutionary? The difference in framing, the choice of language, emphasis, and narrative, matters profoundly. It influences funding, future observations, and public understanding. In essence, the challenge isn't just about the data on ATLAS, but about how we, as a community, choose to tell its story. The balance lies. Loeb's points, often derived from blog discussions and essays rather than peer-reviewed research, encompass a range of intriguing observations and hypotheses. These include noting alignments along the ecliptic and planetary positions, suggesting that ATLAS's trajectory might have been influenced by optimized close approaches, and highlighting the extreme polarization of its scattered light as a potential indicator of artificial origin. Some claims even propose that the material composition of ATLAS could include nickel without iron, an unusual ratio that, although compelling, has not yet gained consensus within the scientific community through rigorous peer review. The core of the argument posits that if one calculates the odds of ATLAS's path coincidentally passing near Mars and Earth at geometries suitable for observation, those probabilities appear to be quite low. When combined with the peculiar chemistry and polarization characteristics, the prior likelihood that all these features could arise through natural processes diminishes further still. Loeb contends that, at some point, the scientific community must consider an alternative hypothesis, that Atlas isn't merely a natural comet but could instead be a probe, a relic, an object crafted by intelligent design. This perspective, however, has met swift and pointed criticism from senior astronomers like Jason Wright, who directs the Penn State Extraterrestrial Intelligence Center. They argue that many of Loeb's methodologies, particularly the way he accounts for selection effects, are flawed. For example, critics point out that calculating the probability of an event after observing it, a practice known as post hoc or posterior probability framing, is a classic statistical fallacy. Essentially, it's a logical misstep to assess the odds of an observed outcome without considering the broader context of how data was gathered or the biases inherent in the detection process. Furthermore, critics highlight that media incentives, particularly the tendency for sensational claims to generate headlines, attract funding, and garner public interest, can create perverse motivations to hype speculative scenarios at the expense of rigorous science. As Wright and colleagues have emphasized, a low-probability event is not necessarily impossible. It remains plausible within the vast parameter space of natural phenomena. However, extraordinary claims like the proposition that Atlas is an artifact demand extraordinary evidence, not merely sensational narratives or speculative hypotheses aimed at capturing attention. The language used to describe Atlas matters because it influences funding priorities and research focus. If the object is labeled simply as an interstellar visitor, it will primarily attract study within planetary science programs, focusing on its physical and chemical properties. Conversely, if it's characterized as a potential technological relic, it might draw interest from SETI, Search for Extraterrestrial Intelligence initiatives, or even prompt concerns about national security, thereby attracting private investment from donors interested in existential or astrobiological questions. The narrative shift can alter mission proposals, influence the allocation of telescope time, and shape the broader scientific discourse. For example, the James Webb Space Telescope did not target Atlas because someone suspected it might be a spaceship. Instead, it focused on its classification as an interstellar comet, leveraging JWST's capability to analyze its volatiles and composition. But if future observations suggest otherwise, the justification for additional targeted studies could be framed differently, and that feedback loop between storytelling and resource prioritization exemplifies how scientific narratives influence and are influenced by funding and institutional agendas. This phenomenon echoes a historical precedent, the case of Oumuamua. When it first passed through our solar system in 2IATLAS, the absence of a visible coma coupled with a slight non-gravitational acceleration led some researchers, Loeb among them, to entertain the possibility of an artificial origin such as a light sail. Loeb's team even published a paper exploring that scenario, which was a thorough technical investigation into the parameter space of such structures. However, media coverage and blogs amplified the idea, elevating it from a speculative what-if to a widely discussed possibility. Public perception shifted accordingly, framing interstellar objects as potentially artificial, until subsequent arrivals like Borisov behaved in a manner consistent with familiar cometary physics, with visible coma and predictable outgassing. By then, the narrative had been set. Interstellar objects could be alien artifacts, or at least they had the potential to be. Atlas inherited that baggage, and the speculation about its artificiality continued to cast a shadow over its interpretation. In essence, Loeb's points exemplify the complex interplay between scientific hypotheses, media narratives, and funding influences, an ongoing challenge in the search for extraterrestrial life and intelligence. Since the discovery of Oumuamua, the first confirmed interstellar object to traverse our solar system, technological and observational capabilities have advanced dramatically, most notably with the advent of the James Webb Space Telescope. Unlike in 3IATLAS, when Oumuamua's data was limited primarily to optical observations, JWST now offers the ability to analyze the chemical composition of interstellar visitors in unprecedented detail, revealing their molecular and isotopic makeup with higher precision than ever before. Ground-based telescopes have also improved significantly, with enhanced polarimetric imaging providing finer resolution and more reliable polarization measurements across a broader range of phase angles. As a result, our data streams for objects like 3IATLAS are richer, faster, and more intricate, which should, in principle, make the debate over whether such objects are natural or artificial somewhat clearer. However, this increase in data volume and quality is a double-edged sword. While it equips us with more information to discern between natural origins and potential artificiality, it also offers more opportunities for both sides in the debate to highlight select data points, whether to bolster their arguments or to cast doubt on the alternative hypothesis. This underscores the importance of maintaining a disciplined approach to scientific inquiry, a stance I want to clarify here. We must treat speculation as speculation, clearly distinguishing between hypotheses rooted in peer-reviewed research and those originating from unverified claims or conjecture. Our goal is to promote empirical tests capable of falsifying both natural and artificial scenarios, recognizing that the most damaging outcome is not exploring a bizarre idea and finding it wrong, but rather neglecting to investigate altogether and missing a genuine discovery. In practical terms, what tests can we perform? First, we should seek repeatable, high-quality polarimetric imagery across a broad spectrum of phase angles. If the unusual negative polarization branch observed in Atlas dust arises from exotic grain properties, such as unique shapes, compositions, or fractal structures, it should be reproducible under different observational conditions and capable of being modeled accurately. Conversely, if this feature is an artifact, perhaps stemming from early geometric assumptions or measurement errors, it should vary with subsequent observations. Second, we need to monitor the evolution of volatile ratios as Atlas approaches perihelion. Natural comets typically exhibit predictable behavior, sublimating and releasing gases in a manner consistent with well-understood thermal physics. If Atlas diverges from this pattern, say, if the CO2 to water ratio remains unusually high or changes unexpectedly during perihelion, that would be a strong indication of anomalous formation or processing history, demanding further scrutiny. Third, post-perihelion non-gravitational orbit fits are crucial. If the parameters A1 and A2, representing the radial and transverse components of non-gravitational acceleration, align with what we expect from cometary outgassing, this would support a natural sublimation-driven origin. On the other hand, if Atlas remains remarkably inert dynamically despite evident activity, showing no measurable acceleration or displaying unusual geometries, this would deepen the mystery and challenge conventional models. Fourth, high signal-to-noise spectroscopy aimed at detecting trace metals in complex organic molecules can help clarify the object's composition. For example, claims of nickel-rich, iron-poor material must be substantiated with calibrated spectra, including error margins, before they can be accepted as scientific fact. Until then, such assertions remain unconfirmed claims, not data. It's also vital to cultivate media literacy in this context. When claims suggest that the probability of Atlas's particular trajectory is 1 in a million, it's essential to question what the search space entails. A figure that sounds impressive can be misleading if it implies a narrow set of possibilities. In reality, we often examine millions of potential scenarios, so such probabilities can lose their significance. Similarly, when someone asserts that a feature is unprecedented, we should consider the sample size, 3 interstellar objects so far, meaning that our statistical foundation is limited. Furthermore, the philosophical principle of Occam's razor reminds us that the simplest explanation, namely that Atlas is a natural object, may involve complex but sufficient assumptions, whereas invoking artificial origin hypotheses demands additional, often extraordinary assumptions such as extraterrestrial engineering or deliberate targeting. These hypotheses require more compelling evidence, not just because they seem exotic, but because their foundational assumptions extend beyond the current scientific paradigm. Nevertheless, even wild ideas serve a valuable purpose. They motivate targeted observations such as dedicated polarimetric campaigns, spectroscopy, or high-cadence photometry, which can reveal subtle features consistent or inconsistent with their hypotheses. If, for example, Atlas's dust exhibits polarization signatures or surface activity patterns that cannot be explained by natural processes, then those observations are invaluable, even if they ultimately support a natural explanation. The key point is that science advances through rigorous testing, not by dismissing unconventional hypotheses outright. If claims about potential artificiality lead to new observations, say a specialized polarimetry campaign or spectral analysis that uncovers unexpected features, then the process of scientific inquiry is fulfilled, regardless of the outcome. What stories can we craft that align with Atlas's intriguing chemistry, polarization signals, motion through the galaxy, and its seemingly untraceable origins? That's the journey we embark on next, because understanding that something is natural does not mean it's mundane or ordinary. In fact, natural phenomena can be remarkably ancient, exotic in their makeup, and profoundly strange, sometimes just as mind-bending as the idea of artificial engineered objects. Let's explore some of these possibilities, which I'll refer to as phantom models. These are working hypotheses, conceptual scenarios that could produce an object like Atlas without necessitating any deliberate or extraterrestrial engineering. Each of these models can explain certain facets of the data, yet none can account for everything perfectly. That's perfectly acceptable in science. Progress often hinges on testing models against observations, rather than waiting for a flawless, all-encompassing theory to appear from the heavens. Scenario 1. Primordial debris from galaxy interactions. Our galaxy, the Milky Way, has a tumultuous history, marked by violent mergers and cosmic collisions. Over cosmic time, it absorbed smaller galaxies. Dwarf galaxies such as Gaia and Enceladus, the Sagittarius dwarf, and others, while we were still mapping the galaxy's structure. When these dwarf galaxies merged with ours, they didn't just deposit stars, they also delivered gas, dust, planetary remnants, and small bodies, debris that was stirred into the galactic halo, or settled into the galactic disk. If Atlas originated from one of these ancient mergers, it could have been wandering through space for billions of years, ejected long before the Milky Way had taken its current shape and structure. This scenario neatly accounts for its old kinematic age and why we cannot connect it to any currently identifiable nearby star. Furthermore, if that dwarf galaxy had a different metallicity or volatile chemistry than the native Milky Way, particularly in its abundance of carbon dioxide or other volatiles, this could explain Atlas's unusual chemical makeup. Is this feasible? Certainly. Is it provable with current data? Not yet. But as our measurements improve, we might one day confirm or refute this possibility. Scenario 2. Rogue planet crush shattering. Imagine a super-Earth or a mini-Neptune ejected from its original planetary system, wandering through the interstellar void for billions of years. At some point, it passes close enough to a star, close enough for gravitational tidal forces to act upon its crust. These forces could fracture the crust, causing shards to break off. If the mantle chemistry favored the formation of carbon dioxide ices, some of those shards might be rich in CO2. Over time, these fragments could become interstellar comets. 3IATLAS might be one such shard, an ejected piece of a larger planetary body. This could explain a potentially large, dense nucleus, consistent with Hubble's upper limit of around 5.6 kilometers, and its peculiar chemistry, especially the high CO2 content. But it's important to emphasize, this is speculative. Currently, we have no direct evidence of rogue planets shattering near stars to produce such fragments. Still, it remains a plausible mechanism, one that fits certain aspects of the data but awaits confirmation. Scenario 3. Post-main sequence ejections. Stars don't live forever. When a star exhausts its hydrogen fuel, it leaves the main sequence and transitions into a red giant. During this phase, the star sheds mass and the planetary system, if it survives, undergoes upheaval. Orbits become destabilized and some planets or planetesimals may fall inward or be ejected entirely. Additionally, the volatile materials, ices and gases, locked in the outer parts of the system can be redistributed or processed thermally. If Atlas was ejected during such a post-main sequence phase, it might carry signatures of this tumultuous history, particularly unusual volatile ratios caused by thermal processing during the star's red giant stage. The abundance of CO2 could be enhanced if carbon and oxygen were plentiful in the star's outer layers, then mixed into the planetary debris as the system reconfigured. This scenario could explain its old age, untraceable origin, and its unique chemical fingerprint, all consistent with a star that has long since evolved beyond the main sequence. In essence, these models suggest that Atlas is not necessarily a product of recent planetary formation or a deliberate artifact, but could be a relic of ancient galactic events, stellar evolution, or planetary cataclysms, each pathway offering a glimpse into processes that have shaped the cosmos over billions of years. While none of these scenarios can yet be conclusively proven, they demonstrate that the universe's history is rich and layered, sometimes stranger and more exotic than anything engineered by intelligent design. This series of hypotheses offers compelling explanations for Atlas's advanced age, its elusive origin, especially if the parent star has since become a faint white dwarf, and its peculiar chemistry. Yet it's crucial to recognize that these are possibilities, not certainties. They remain in the realm of could be, not did happen. Let's consider Scenario 4. The idea of molecular cloud condensation forming dark comets. Though this concept is a niche and not widely embraced within the astronomical community, it's worth mentioning due to its intriguing implications. The core idea is that smaller bodies, rather than full-fledged planets, might directly condense within the dense filaments of molecular clouds, bypassing the typical process of star and planetary system formation. These tiny icy fragments would originate as parts of prestellar cores, forming in the coldest, densest pockets of interstellar space. Over time, they could be dispersed when the parent cloud is disrupted, perhaps by nearby star formation episodes or supernova shocks. If Atlas indeed formed through such a process, its chemical makeup would likely reflect the composition of the molecular cloud environment in which it was born. This might include a high carbon dioxide content, dependent on the local abundances of carbon and oxygen in that specific cloud. However, it's important to note that this mechanism remains highly model-dependent and controversial. The prevailing view among most astronomers is that small bodies generally require a protoplanetary disk, an environment rich in gas and dust orbiting a young star to form, rather than material directly condensing out of a molecular cloud. Consequently, this hypothesis is considered speculative, even within the realm of phantom models that challenge conventional thinking. Moving on to Scenario 5. Another fascinating but more speculative idea involves the notion that Atlas may not originate from our galactic disk at all. Instead, it could be an intergalactic traveler that was captured by the gravitational potential of the Milky Way's halo billions of years ago. In this scenario, Atlas would have orbited in the halo for an immense span of time, possibly eons, before some perturbation caused it to drop into the galactic disk recently. This could explain why its kinematic properties appear consistent with the thin disk now despite lacking a nearby stellar parent, and why it seems so old. Its journey predates the formation of our current stellar neighborhood. Proving such a scenario is inherently difficult as we cannot reliably trace halo orbits over such vast timescales. Nonetheless, conceptually, it remains feasible. The chemical signature of Atlas would depend heavily on where it originally formed, possibly in a satellite galaxy, or even in intergalactic space if such formation events are plausible. Now, how do these models compare against the current data? The star's remarkable CO2 to water ratio of approximately 7.6 suggests a distinctive formation history. Models 2 and 3, post-main sequence ejections and rogue planetary shards, offer plausible explanations for this abundance profile, potentially through mantle composition or processes occurring after the star's main life cycle. Model 1, which interprets Atlas as remnant debris from a primordial dwarf galaxy merger, also aligns with the star's age and kinematic properties but hinges on specific chemical assumptions about the dwarf galaxy's makeup. Model 4, involving direct formation in a molecular cloud, remains the most speculative, while Model 5, the halo capture hypothesis, presents an intriguing but challenging to test concept, especially given the lack of observable current signatures. Looking ahead, what future observations could help distinguish among these models? One promising approach involves analyzing dust size distribution through post-perihelion photometry. As Atlas approaches perihelion, measuring how its brightness diminishes with increasing distance can yield insights into the typical sizes and properties of the dust grains, information that can constrain their formation processes and environmental history. In addition, detailed spectroscopic studies at various wavelengths could reveal isotopic ratios or trace species, such as deuterium to hydrogen or carbon isotopes, that serve as chemical fingerprints helping us pinpoint Atlas's birthplace. Observations of any potential fragmentation or activity changes as it warms could also shed light on its internal structure and composition, further refining hypotheses about its origin. In essence, while the current data leaves many questions open, each future measurement carries the potential to validate or challenge these scenarios, bringing us closer to understanding the true story behind this enigmatic interstellar visitor. If we can accurately gauge how the brightness of Atlas diminishes as it recedes from us, it opens a window into understanding the size distribution of its constituent dust grains. Such information is crucial because grain size influences how particles stick together, coagulate, and thus shapes the history of material aggregation in its original environment. Beyond that, by analyzing volatile isotope ratios, specifically the ratio of deuterium to hydrogen, the proportion of carbon-13 to carbon-12, and nitrogen-15 to nitrogen-14, we can obtain chemical fingerprints that reveal the environmental conditions during its formation. These ratios serve as cosmic thermometers and chemical markers indicating the temperature and elemental makeup of the region where Atlas originated. Additionally, conducting deep, high-resolution imaging to observe fragmentation patterns can provide insight into the structural integrity of the object. Should Atlas begin shedding pieces as it warms during its approach to the Sun, these fragments would offer clues about its internal cohesion, information that directly relates to its formation history and the processes that shaped it. While these measurements are challenging, requiring precise instrumentation and meticulous analysis, they are certainly within the realm of possibility with future advancements in observational technology. From this, a key takeaway emerges. Even with the complexities involved, more than one natural evolutionary path can lead to an object exhibiting the chemical composition of carbon monoxide, CO, which is both remarkably rich and, intriguingly, untraceable to any current stellar parent. This means we do not need to invoke artificial engineering or deliberate design to explain the properties of interstellar objects like Atlas. Instead, we must accept that such objects can originate from diverse and poorly understood environments and dynamical histories across the galaxy. This realization is profoundly exciting because it positions every interstellar visitor as a messenger, an emissary from a distant, unreachable corner of the galaxy, carrying within it the story of environments and processes we have only begun to fathom. These objects serve as physical relics, offering insights into galactic evolution, planetary formation, and the variety of cosmic conditions that prevail beyond our direct reach. Now let me push this line of thought even further. What if Atlas isn't merely old, but truly ancient? What if it predates the formation of our solar system, possibly existing before the Milky Way's current structure took shape? What if Atlas is a cosmological outsider, a relic originating from the very early universe, an artifact from the primordial epoch of star and planet formation? Considering the kinematic data that suggests its age, estimates place Atlas somewhere between 3 and 11 billion years old. The lower end of that range makes it older than the Sun itself, which is about 4.5 billion years old. The upper end approaches the age of the universe, which stands at approximately 13.8 billion years. To put this into perspective, the Milky Way's disk started forming roughly between 10 and 12 billion years ago. If Atlas is at the older end of these estimates, it would have come into existence when the galaxy was still in its infancy, an era characterized by lower metallicity levels and the initial phases of planet building around the earliest generations of stars, known as population 2 stars. It is essential to clarify, however, that these age estimates are inherently statistical rather than definitive. We infer them indirectly by examining how much Atlas's motion has been scattered or dispersed relative to the local standard of rest, a measure of how much its velocity has been kicked around over cosmic time. This approach produces a probabilistic estimate of age based on population models, akin to a cosmic form of statistical fingerprinting. It is not a precise measurement like carbon dating, where a specific number is assigned. Nonetheless, even with these uncertainties and the inevitable error margins, the results compellingly point toward an object that is genuinely old, potentially older than most structures we associate with our galaxy's current configuration. Thus, the question becomes, could Atlas be among the earliest solid objects formed in the galaxy? Might it be a first-generation planetesimal from a low metallicity system? Early stars, especially those formed in the galaxy's first billion years, contain significantly less iron, silicon, and other heavy elements typically linked to rocky planets. However, they still produced oxygen and carbon, elements forged in the nuclear furnaces of the earliest stars and distributed through the galaxy via supernova explosions. A planetary system that formed around such a primordial metal-poor star might exhibit a markedly different chemical composition from familiar systems like ours. Its materials could be enriched in volatiles like CO, carbon monoxide, relative to silicate minerals reflecting the unique conditions of its birth environment. In essence, this line of reasoning suggests that Atlas might be a relic from an ancient, primitive epoch, perhaps a fragment of a planetary building block that originated in a low metallicity neighborhood of the galaxy, long before the more chemically evolved systems we observe today. This hypothesis not only aligns with the statistical age estimates, but also offers a tantalizing glimpse into the diversity of planetary formation environments, stretching our understanding of what is possible in the cosmic timeline. If Atlas truly originates from an ancient environment, its chemistry could tell a compelling story. An excess of volatiles relative to rock, particularly a higher abundance of carbon and oxygen compounds, would support the idea that it formed in a colder, more primordial region of a planetary system, possibly beyond the typical frost line for CO2, where volatile ices are more prevalent. Specifically, a dominance of CO2 over silicate minerals would suggest formation in a frigid zone, where volatile compounds remained frozen and abundant, rather than being depleted or altered by warmer conditions. However, the challenge lies in the current limitations of our data. To definitively confirm such a chemical signature, measurements of isotope ratios are essential. These ratios act as the universe's forensic clues, offering a glimpse into the environment and processes that shaped the object during its birth. The most straightforward of these is the deuterium to hydrogen ratio, D to H, which was established during the primordial nucleosynthesis shortly after the Big Bang. While this ratio provides a baseline, stellar processing and local chemical reactions can modify it over time, complicating its interpretation. More informative are the isotope ratios of heavier elements, namely carbon-13 to carbon-12 and oxygen-18 to oxygen-16. These ratios encode subtle clues about the temperature, pressure, and chemical environment during formation. Variations from the canonical solar system ratios would indicate that Atlas originated in a region with a distinct chemical history, perhaps in a low metallicity early galactic environment, which formed stars and planetary bodies under different conditions than those found in our neighborhood. Unfortunately, we do not yet possess the high-fidelity isotope data needed to test these hypotheses. The spectroscopy capabilities of the James Webb Space Telescope are impressive, but pulling out the fine spectral lines required to measure isotope ratios demands exceptionally high spectral resolution and a signal-to-noise ratio that we currently cannot achieve for such faint and distant objects. It's possible that after perihelion, when the comet's coma brightens, astronomers might attempt to obtain these measurements. But for now, acquiring such data remains a pending wishlist item. To appreciate why isotopes matter, consider the following background. The Big Bang primarily produced hydrogen, helium, a small amount of lithium, and the isotope deuterium. Heavier elements, and their isotopic ratios, arose later within stars through nuclear fusion processes, when stars fuse hydrogen into helium, and then helium into carbon or oxygen. They generate specific isotope ratios that depend on the internal temperatures and pressures. When supernova explosions occur, they release these isotopes into the surrounding interstellar medium, enriching it. New stars then form from this chemically enriched gas, and planets coalesce from the residual debris. The isotope ratios in planetary bodies, including comets, reflect the composition of the original gas cloud from which they formed. Therefore, measuring isotopic ratios in a comet like Atlas provides a direct fingerprint of its birth environment. In our solar system, comets tend to have isotope ratios close to solar values because they originated from the same primordial cloud as the Sun. If Atlas's ratios deviate significantly, say, showing a lower deuterium content or unusual carbon or oxygen isotope ratios, it would strongly suggest an origin elsewhere in the galaxy, perhaps in a different kind of stellar nursery or even in an earlier epoch of galactic history. Looking at the broader galactic context, the Milky Way's structure adds further nuance. The galaxy comprises several stellar populations: the relatively young, metal-rich thin disk where our solar system resides, the older, more metal-poor thick disk, and the even more ancient halo populated by stars and debris from the galaxy's earliest days and past mergers with smaller satellite galaxies. Atlas's kinematics, its motion through the galaxy, indicate it belongs to the thin disk, but with a surprisingly large peculiar velocity, pushing it toward the boundary between thin and thick disk populations. This is not unusual for older objects, as billions of years of gravitational interactions, stellar encounters, spiral arm passages, and accretion events can stir stars and objects from their original orbits. Such a velocity signature suggests that Atlas could be a thick disk object that was scattered into a more circular, thin disk-like orbit, or perhaps an ancient thin disk object that has accumulated significant velocity kicks over time. However, kinematic data alone cannot reliably specify its origin. When combined with chemical clues, particularly its CO2 richness and dust properties, the picture becomes clearer. Stars and stellar populations formed in metal-poor environments tend to produce bodies with volatile-dominated compositions, such as high CO2 content, because of the relative scarcity of silicate material. If Atlas's chemistry indicates a low metallicity origin, it would favor the hypothesis that it formed in a primordial early universe environment, possibly in a region of the galaxy that formed before the enrichment of metals typical of later generations of stars. This would imply that Atlas is a relic from the galaxy's infancy, a surviving fragment of the earliest planetary building blocks now wandering through space. In essence, the combination of its unusual, this notion is of course highly speculative, yet it remains a line worth exploring. Should future evidence confirm that Atlas predates the formation of the solar system, if it indeed turns out to be older than the Sun itself, it would fundamentally reshape our understanding and narratives about such objects. Our current perspective tends to view comets as native to our solar system, remnants from the primordial cloud that coalesced to form our star and its planets. Interstellar objects, in contrast, are generally regarded as foreign visitors, strangers from other stellar systems but still relatively recent arrivals, formed around stars of similar age within particular epochs of galactic history. However, if Atlas proves to be an ancient interstellar traveler, an elder wandering the galaxy long before the solar system came into being, it would challenge that assumption. Instead of being a recent interloper, it would be an elder, a survivor from an earlier era of the galaxy's evolution. It would have been traversing the vastness of space at a time when the molecular clouds that eventually birthed our sun had yet to even begin their collapse. This means it would have witnessed star formation events that we will never see firsthand, carrying with it a chemical signature from a bygone epoch of galactic history. An era from which we can only infer conditions by examining the spectra of ancient stars and stellar remnants. Such a discovery would be profoundly humbling, reminding us of the deep history embedded in the galaxy and our limited ability to fully comprehend it. But it's essential to approach these ideas with caution. We should avoid overclaiming, especially regarding the concept of pre-galactic origins for Atlas. Presently, there is no concrete evidence to suggest that Atlas formed before the universe itself, or before the galaxy took shape. The universe had already assembled many galaxies by the time Atlas could have come into existence, making it a galactic object, an ancient wandering piece of the galaxy's fabric, rather than a relic from a time predating the galaxy's formation. This thought experiment is therefore more about considering whether Atlas is older than most galactic structures we routinely observe and study, rather than asserting that it predates the very existence of galaxies themselves. It's important to keep our ideas grounded in current evidence and avoid drifting into unfalsifiable speculation. To illustrate this concept, imagine a timeline stretching back from the dawn of time itself. The Big Bang occurred approximately 13.8 billion years ago, marking the birth of the universe. A few 100 million years later, the first stars ignited, furnaces of cosmic activity that began to forge the elements. About 12 billion years ago, The halo of our galaxy, the Milky Way, started to take shape, followed by the formation of its thick disk, which emerged roughly between 10 and 12 billion years ago. The thin disk, where our solar system resides, formed around 8 to 10 billion years in. Our Sun itself is approximately 4.6 billion years old. Now place Atlas on this grand timeline, complete with error margins. Its lower age estimates hover around 7 billion years, while the upper bounds stretch beyond 10 billion years. Consequently, Atlas spans an intriguing interval, its existence bridging the epoch of our Sun's birth and the galaxy's early years, making it akin to a time capsule, an ancient artifact with a scratch label from deep cosmic history. Why does this framing resonate so strongly with audiences? Because it offers a profound recontextualization of the object's significance. It's no longer just a comet or a wandering rock. It becomes a message in a bottle from deep time, a tangible piece of the galaxy's ancient past. Physical proof that the galaxy is older and more complex than our current understanding allows. It bridges the vast, abstract concept of cosmic time with something concrete, an object that we can observe with telescopes, a relic we can study directly. This powerful connection invites us to reach across billions of years, to touch something ancient, and in doing so it stirs a sense of wonder and humility. Yet, as compelling as this narrative is, it's crucial to recognize its limitations. If Atlas is not a transmitter, if it is not intentionally broadcasting signals, then it may still be a carrier of information, but not in the form of deliberate messages. Instead, it could encode information in its very structure, its chemistry, or even in subtle features like polarization. These ideas form the premise of the next speculative chapter, one that lives firmly in the realm of hypothesis but is interesting enough to consider because it is, at least in principle, testable. Part 13. The Hidden Communications Hypothesis. Let me clarify up front. What follows is purely speculative. There is no peer-reviewed evidence to suggest that Atlas is an artificial construct or that it is intentionally transmitting information. Currently, all data points, its trajectory, chemistry, polarization, and activity are consistent with natural origins. This is not to dismiss the intriguing patterns and anomalies observed, but to frame them within the bounds of scientific hypotheses that require rigorous testing before jumping to conclusions. This thought experiment ventures into the realm of the speculative, exploring how one might embed information within a passive object and what observational signatures could reveal such encoding. While it borders on science fiction, it remains firmly rooted in the principles of physics and current observational techniques, making it an intriguing puzzle rather than a claim. The concept of non-signal intelligence, where information isn't actively broadcast but stored passively, has long been contemplated within SETI circles. Traditionally, SETI efforts focus on detecting electromagnetic signals, radio waves, laser pulses, or other deliberate beacons that indicate intentional communication. However, a different school of thought considers the possibility that objects could encode information in their physical structure or surface properties, effectively serving as silent carriers of data. Imagine a probe that encodes its original purpose or origin in the way it interacts with light, perhaps through the scattering pattern of its surface, the reflectivity at specific wavelengths, or even the geometry of its orbit around a star or in interstellar space. Such an object wouldn't require onboard power, electronics, or active transmission systems. Instead, it would rely on meticulous initial design, crafted to produce subtle yet discernible signals detectable by an observer with the right tools and knowledge. This raises the question, how could information be hidden in polarization? Polarization, the orientation of light's electric field, depends on a variety of factors: grain size, shape, porosity, chemical composition, and the scattering angle. If one could precisely control the microstructure of dust grains or surface features, it would be theoretically possible to engineer a polarization phase curve with specific characteristics. For instance, one might design a dip in polarization at a particular phase angle, an inversion at another, or modulate the depth and width of these features across different wavelengths. To the untrained observer, these signals would appear as natural dust scattering phenomena. But to an informed observer, aware of the potential for intentional design, they could encode metadata, precise coordinates, timestamps, or signatures indicative of origin or purpose. The challenge lies in distinguishing such designed modulation from natural variation. Natural dust scattering produces characteristic polarization curves which can include dips, peaks, and inversion points, all resulting from the inherent properties of dust grains and their interactions with light. For example, Atlas's polarization curve features a narrow, deep negative branch at about 7 degrees phase angle, inverting around 17 degrees, an unusual but explainable natural phenomenon. It's unlikely that this specific pattern is an intentional signal. Instead, it probably results from the dust's microstructure. However, as a thought experiment, if one aimed to embed information within this curve, it would require high-cadence polarimetric measurements across many wavelengths and phase angles. Researchers would search for deviations from smooth, natural models, sharp features or irregularities that don't match typical grain distributions. They might also look for periodic modulations correlating with the object's rotation or orbital phase, which could serve as a form of code. So far, no such features have been observed in the interstellar object known as 3I. Its polarization remains consistently unusual yet explainable within the framework of natural, if exotic, dust models. Another potential method for encoding information involves dust jets and anti-tails, faint extensions of dust that sometimes point toward the sun rather than away. These features, caused by large dust grains on specific orbital geometries, can produce subtle asymmetries. If one could control the timing and direction of dust release, it might be possible to create patterns, variations in brightness over time or angle, that serve as a kind of silent barcode. Detecting such patterns would require high-resolution, time-resolved imaging capable of tracking the coma's evolution over hours or days. The goal would be to identify structures or sequences, such as pulses or directional jets, that don't fit the expected behavior produced solely by solar heating and hydrodynamics. In the case of 3I, no such barcode or sequence has been reported. Its coma appears asymmetric and sunward enhanced, consistent with natural solar heating effects. The absence of detectable structured dust release patterns suggests that, if a deliberate encoding exists, it remains hidden or undetectable with current observational capabilities. Nonetheless, this line of thought opens fascinating possibilities. Silent, passive objects could, in principle, carry embedded information, awaiting discovery through careful, high-resolution, and multi-wavelength observations. Ultimately, the challenge of detecting such passive encoding lies in the subtlety of the signals and the natural variability inherent in cometary and dust-scattering phenomena. Yet, contemplating these possibilities pushes the boundaries of our understanding and encourages the development of more sophisticated observational strategies. While no evidence currently suggests such intentional encoding in interstellar objects, the very idea underscores the importance of detailed polarization and dust studies as potential windows into a universe where silence may conceal stories, and where even the most unassuming objects could be carriers of hidden meaning. In the realm of speculative ideas about interstellar objects, some have proposed the intriguing possibility of silent probes, sometimes called Bracewell probes, conceived as autonomous explorers sent by advanced civilizations. These hypothetical probes would not broadcast signals until they detect signs of intelligent life, essentially lying in wait, observing and recording from a passive stance. If Atlas were such a probe, it would now be in a state of silent observation, monitoring its surroundings, gathering data, yet refraining from any form of signaling or active communication. So how might we go about testing this fascinating hypothesis? The first step would be to actively search for responses, attempting to establish any form of two-way communication. This could be done by transmitting signals aimed at Atlas to see if it responds in kind, perhaps through some encoded reply or anomaly. Next, careful scrutiny of its trajectory would be essential. Any deviations from what natural forces would produce could hint at artificial influences, subtle nudges or corrections inconsistent with gravitational or cometary activity. Moreover, continuous monitoring for emissions beyond normal cometary phenomena, such as gamma rays, neutrinos, or other exotic particles, could reveal hidden signals or signatures that do not originate from natural processes. In terms of specific data that could indicate intentional encoding, scientists could analyze multiband polarization patterns across a broad spectrum, optical, near-infrared, and mid-infrared wavelengths, to detect whether the polarization features exhibit correlations or anomalies that defy natural explanations. High time resolution observations could be employed to search for periodic brightness variations, akin to binary signals or coded sequences embedded within the comet's activity. Spectroscopic studies of the dust and gas surrounding Atlas might reveal absorption or emission features from materials that are unusual or inconsistent with natural comet compositions, such as metals that are not oxidized or complex organic molecules that seem artificially assembled. Additionally, radio telescopes could be used to scan for signals across a wide spectrum, seeking any form of communication or emission that might have gone unnoticed. All these measurement strategies are within the realm of current or near-future technological capabilities, and some have already been attempted during the observation campaigns. Yet so far, no anomalous signals or signatures have been detected that would suggest intentional encoding or communication. Where then does the hypothesis of Atlas as a silent encoded probe likely fail? The principle of Occam's razor guides us here. Natural phenomena provide sufficient explanations for the observed properties. The polarization patterns can be understood through natural scattering processes. The coma's composition and activity align with known cometary physics, and the trajectory can be explained by gravitational interactions without invoking artificial influences. To claim that Atlas is an engineered artifact, one must demonstrate features that cannot be accounted for by natural processes, an extraordinary burden of proof. Currently, Atlas does not exhibit any such definitive indicators. Its unusual properties, while intriguing, are consistent with natural variability and phenomena. So why dedicate space to this speculative scenario? Because exploring these possibilities motivates us to develop and implement extraordinary measurements. If the hypothesis that Atlas encodes information prompts new observational campaigns, such as more detailed polarization studies or sensitive radio surveys, and these investigations find nothing anomalous, they nonetheless advance our understanding of the object's true nature. Science progresses not solely through confirmation, but also through the systematic elimination of unlikely hypotheses. Taking the idea of encoding seriously enough to test it exemplifies scientific rigor and honesty, and it ensures that we do not dismiss unconventional ideas prematurely. In conducting such tests, transparency remains paramount. Scientific communication must distinguish clearly between peer-reviewed findings and opinionated speculation. When references to claims of encoding appear, they should be contextualized with appropriate citations, whether from published research or from speculative blogs, so that the scientific discourse remains trustworthy. This methodical approach maintains integrity and ensures that extraordinary claims do not distort the scientific process. In the end, the universe is full of natural phenomena that can appear strange and perplexing. The universe's inherent weirdness does not necessarily imply artificiality. While the idea that Atlas might be a deliberately silent or encoded probe is an intellectually stimulating thought experiment, the current evidence aligns more convincingly with a natural object exhibiting unusual but explainable properties. Nonetheless, the process of testing these hypotheses, however improbable they may seem, embodies the spirit of scientific inquiry. Curiosity driven by rigor, openness to new ideas, and a commitment to uncovering the truth through careful, evidence-based investigation. The peculiar qualities exhibited by objects like Atlas, though initially unsettling, are actually what we should expect when we consider the astonishing diversity inherent in planetary systems scattered throughout the galaxy. Each stellar environment is unique, shaped by its own history, composition, and dynamic processes. As a result, every interstellar visitor we encounter will inevitably surprise us, challenging our assumptions and expanding our understanding. Such surprises should not be immediately interpreted as signs of artificial origin or extraterrestrial engineering. Instead, they serve as a stark reminder of how limited our current knowledge truly is, how much we have yet to learn about the universe's myriad configurations. Whether Atlas is a product of natural processes or something more, an artifact, a shard, or an ancient relic, its very existence compels us to rethink fundamental notions of cause and origin. It pushes us to confront the boundaries of what we can know, illuminating the profound distinction between the mere existence of an object and our ability to trace its past. There is a philosophical dimension embedded in this challenge, a recognition that some aspects of the universe may forever remain beyond our reach, not because they are intentionally hidden, but because the universe's own workings have rendered their histories irretrievable. This brings us to what I will call the philosophical singularity, the core enigma at the intersection of science, knowledge, and understanding. Let me restate the central question as plainly as possible. Atlas, a tangible physical entity, undeniably exists. It has mass, a well-defined trajectory, and a distinct chemical composition. It is real. Yet within the scope of our current data and observational horizon, it bears no traceable past. We cannot link it back to a parent star or stellar system. We cannot identify a specific stellar encounter that ejected it into interstellar space. We are unable to reconstruct the chain of gravitational interactions, billions of years of cosmic history, that ultimately brought Atlas to our vicinity. The object's existence is undeniable. Its history, however, is effectively lost, not because that history did not happen. Causality remains intact in principle, but because the universe's own processes of information dispersal have rendered that history inaccessible. The cosmos's bookkeeping system, so to speak, has scrambled the ledger beyond our capacity to read. This is not a paradox in the strictest sense. Physics allows for causes to have occurred. Atlas was ejected from a planetary system, a process driven by some cause, and that cause was rooted in a star that at some point existed or still exists somewhere in the galaxy. The orbit that carried Atlas into our neighborhood was shaped by an intricate ballet of countless gravitational interactions spanning billions of years. All those processes took place, causality was satisfied. Yet the ability to reconstruct that causal chain from present-day observations can, indeed, often does, fail. This failure is not due to some cosmic concealment. Rather, it reflects a fundamental principle. Information dissipates over time, and with it, the capacity to reconstruct origins. Entropy, the measure of disorder, inevitably wins in the cosmic ledger. Chaos in its relentless march ensures that the detailed record of past interactions becomes indistinguishable from randomness. The universe, in its impartiality, owes us no guarantee of a complete history. It simply does not provide it. To illustrate this point, consider a simple analogy. Imagine you stumble upon a glass bottle on a beach. It's real, made of glass, encrusted with barnacles, filled with water. But there's no message inside, no inscriptions, no markings, nothing to tell you its provenance. You attempt to trace its origin by modeling ocean currents and winds, running the drift backward in time. Yet the ocean is a chaotic place. Currents shift, storms swirl, eddies form and dissipate. Over decades, these processes introduce an ever-growing uncertainty in your simulation. When you try to rewind the bottle's journey through the ocean, the possible starting points spread out so vastly that the original origin becomes entirely unknowable. It could have come from any point along a vast stretch of coastline. Its source is effectively lost to the randomness of chaotic mixing. Atlas is the cosmic equivalent of that bottle. The galaxy is the ocean, vast and turbulent, and 10 million years is a long, long drift. The original stellar system that ejected Atlas has become indistinct in the sands of cosmic time. The universe's own entropy has erased the detailed trail, leaving only the faint echo of existence. The object remains real, but its history is irretrievably scrambled. I will invoke a few physics concepts, lightly as metaphors rather than literal claims, to deepen this analogy. For example, the notion of retrocausality, the idea that in some frameworks of quantum mechanics or relativity, effects can sometimes precede causes, is a fascinating if speculative concept. Similarly, the theoretical possibility of closed time-like curves, solutions to Einstein's equations that, in principle, allow for looping back in time, reminds us that the fabric of space-time itself might, under certain conditions, time, in many modern physical theories, is considered not a fundamental backdrop, but rather an emergent property arising from the increase of entropy, a measure of disorder within the universe. That is, the flow of time is a phenomenon that results from the universe's tendency toward higher entropy states, rather than an independent intrinsic dimension woven into the fabric of reality itself. However, when it comes to Atlas, the third interstellar visitor, this conceptual framework doesn't quite fit. Atlas is a classical object, a tangible entity moving through the well-understood realm of classical space-time, obeying the laws of Newtonian physics and Einstein's relativity. Its motion adheres to the predictable equations that govern how objects travel in a smooth, continuous fabric of space and time. Yet when we attempt to interpret causality, the chain of cause and effect, things become more complex. Our metaphors for understanding how causes lead to effects often rely on the idea that these chains are traceable and continuous. But in the case of Atlas, the causal history appears untraceable. Physics allows for the existence of causes that we cannot reconstruct. The laws permit such scenarios, but the information that records the precise chain of events has become inaccessible. This discrepancy between what physics enables and what information we can retrieve highlights a crucial philosophical and scientific boundary. From a cultural and mythological vantage point, we can revisit the archetype of the wandering stone. Across countless cultures, stories speak of stones that fall from the sky. Meteors, meteorites, or celestial stones that arrive from the void. Some myths frame these stones as messages from divine beings carrying hidden meanings or warnings, while others see them as omens, portents of change or catastrophe. Modern science classifies these objects as meteorites or comets, fragments originating from known celestial processes with origins we can, at least theoretically, trace through their trajectories, compositions, and the stars from which they might have come. Atlas, however, shatters this pattern. It is a wandering stone that defies our attempts at tracing its origins. Its trail is effectively lost, and this loss resurrects the mythic archetype. not because we abandon scientific rigor, but because we confront a fundamental limit that mythic narratives have long acknowledged. Some travelers leave no map, no trail, no record. This echoes a core principle in the philosophy of science. Absence of evidence is not evidence of absence. Just because we have not found Atlas's parent star or origin point doesn't mean it does not exist. It merely reflects the current limits of our observations and tools. The problem arises when our catalogs and observational reach are inherently incomplete. Our current techniques, despite their sophistication, impose a ceiling, say 10 million years, beyond which we cannot reliably reconstruct the object's history. When the search radius is limited and the data sets are incomplete, the notion of an absence of evidence morphs into what feels like a hard, epistemic barrier. It's not that we are ignorant, rather our instruments and methods are limited. This distinction is vital, as ignorance can be remedied with more effort, better tools, and more data. But limitations necessitate the development of entirely new approaches. What does Atlas reveal about the state of our current scientific tools? Consider Gaia, the crown jewel of stellar mapping. It has charted over 1 billion stars with unprecedented precision, measuring positions, motions, and parallaxes. Yet it's constrained by thresholds. Radial velocities are only available for the brightest stars, and parallax measurements are limited to relatively nearby stars. If Atlas's parent star is a faint red dwarf located 500 parsecs away, with no measured radial velocity, Gaia's data simply cannot reveal its presence, even if we searched forever. Mapping the interstellar medium, the gas and dust that fill our galaxy, is even sparser. We lack detailed three-dimensional maps of density and velocity along arbitrary sight lines. Without these, modeling the drag forces and perturbations that might have influenced Atlas's trajectory is impossible. These are not insurmountable obstacles, rather they are technical challenges waiting for the next generation of surveys and missions. The solutions involve deeper sky surveys, more comprehensive proper motion catalogs extending to fainter stars, advanced tomography using background quasars and pulsar signals to chart the three-dimensional gas distribution, and refined galactic models that incorporate dark matter substructures and dynamic features like spiral arms. These advancements are within reach, provided adequate funding and time. The core scientific principle remains. The triad of chemistry, polarization, and dynamics forms a set of keys that can unlock Atlas's secrets. Each provides a different perspective. Composition hints at formation environment, polarization reveals dust processing and environmental history, and dynamics traces its journey through the galaxy. Together, these keys may eventually lead us to a coherent narrative about its origin, even if one or more pathways remain blocked by current technological limitations. Imagine a universe where the key to understanding an interstellar visitor isn't a single piece but a combination of clues, each revealing a fragment of its story. Two keys alone cannot unlock the vault of its origins: chemistry, polarization, and dynamics. Chemistry in this case is peculiar yet suggestive. It hints at the environment where this object might have formed but doesn't give a definitive answer. Polarization, on the other hand, provides insights into the dust grains, how they are structured, their processing history, and remains somewhat enigmatic, yet explainable within known physics. The dynamics, however, prove elusive. They refuse to trace a clear path back through the galaxy's vast history. In essence, we possess two keys and both are partially turned. One offers a tantalizing glimpse, the other hints at a story but remains locked tight. The third, vital key, our understanding of its origin based on motion and gravitational interactions, is rusted shut. What we're left with is a rough sketch, a partial portrait rather than a complete detailed masterpiece. And here lies the emotional core of the story. Because science is not purely a cold, sterile pursuit. It's driven by human curiosity, by feelings, by wonder. Atlas emerges as a messenger from an epoch spanning from 3 billion to 11 billion years ago. It has journeyed farther and endured longer than any human artifact ever could. It has witnessed more stars, more nebulae, more supernovae than any of us can count or comprehend. The object carries within it the chemistry of a world we will never visit, the signature of a system we will never map, and a history that we are forever unable to retrieve. And that realization, profound and humbling, fills us with awe, not despair or nihilism, but humility. It reminds us that the universe is vast, ancient, and intricately complex, far beyond the limits of our current data and understanding. And that's perfectly acceptable. Our limitations are not failures. They are horizons, boundaries pointing us toward new questions, new places to look, new depths to explore. We have pushed Atlas back as far as our tools allow, analyzing its coma, its dust, its motion, and entertained a range of wild hypotheses. Some we have dismissed, others remain on the table waiting for better data. But the story does not conclude with analysis alone. In truth, the narrative ends only when the object departs, because Atlas didn't come to stay. It arrived, it passed through our neighborhood, and now it's heading back out into the dark, into the unknown. And what it leaves behind are not definitive answers, but a collection of richer, deeper questions. Let me craft a picture to illuminate the ongoing mystery, what I call the infinite drift. Imagine the night of September 29th to the 30th, 2025. On that night, Atlas streaks past Mars at a distance of approximately 29 to 30 million kilometers, a fleeting visitor in our cosmic backyard. Fleets of orbiting spacecraft observe, capturing every detail. Mars Express tilts its cameras, MAVIN records plasma interactions, and surface rovers attempt to glimpse the faint trail, though it remains invisible to the human eye. As the days turn toward October 29th and 30th, the moment of perihelion, Atlas reaches its closest approach to the Sun at about 1.36 to 1.4 astronomical units. Solar heating intensifies and buried water ice, if present, should begin to sublimate. The ratio of carbon dioxide to water vapor in its coma is expected to shift, and perhaps non-gravitational acceleration might become detectable. Every moment is watched with relentless precision, Earth-based telescopes orbiting observatories tracking its every move. Then Atlas curves outward again, past Earth, past Mars once more, heading toward the asteroid belt, then onward toward Jupiter's orbit, and ultimately slipping back into interstellar space. This voyage, this passage through our solar system, is a fleeting chapter in its grand journey. Now distilling what we can confidently state, the ground truths of the case. First, no parent star has been identified. In the recent decade, Perez-Couto and their team simulated 10 million years of orbital histories against data from millions of Gaia stars, flagging 93 potential encounters. Yet none proved dynamically significant. The closest star passed at a distance producing an imperceptible velocity change, merely 0.5 millimeter per second, far too small to explain Atlas's current trajectory. Second, the coma itself presents a peculiar chemistry. The James Webb Space Telescope measured a CO2 to water ratio of approximately 7.6, plus or minus 0.3, among the highest ratios ever observed in any comet. This dominance of CO2 at about 3.3 astronomical units from the Sun defies expectations. Water should be the prevailing volatile at that distance, yet Atlas's coma tells a different story. And third, the polarization data adds to the enigma. The measurements indicate, imagine observing an interstellar visitor at a phase angle of merely 7 degrees, where the polarization of its scattered light reaches an extraordinary minimum of approximately -2.7%, an inversion occurring at 17 degrees, an event of unprecedented narrowness and depth in the realm of celestial phenomena. Such a polarization feature has no known equivalent among our catalogued solar system objects. Despite this activity, no non-gravitational acceleration has been detected in its orbit thus far. The comet's coma is active and exhibits a sunward asymmetry, consistent with sublimation-driven outgassing, yet the orbit remains remarkably stable, showing no signs of a measurable rocket effect at this stage. However, this could change as the object approaches perihelion. The size of the nucleus remains uncertain. The upper limit established by the Hubble Space Telescope hovers around 5.6 kilometers, but it could be as small as a few hundred meters. The coma's veil obscures direct measurement, leaving the true dimensions elusive. What might we still learn after the perihelion passage? One key question is whether the activity pattern, specifically the water vapor emission, intensifies. If the ratio of CO2 to water vapor diminishes as the nucleus warms, that would lend support to thermal delay models indicating a surface or subsurface lag in sublimation. Conversely, if the ratio remains high, it would reinforce the hypothesis of an intrinsically unusual composition. Another crucial aspect to monitor is the appearance of non-gravitational forces. If parameters, designated as A1 and A2, begin to manifest in the orbital fit, especially if they correlate with activity asymmetries such as water jet emissions, understanding of natural comet physics would be reinforced. On the other hand, should activity continue without detectable orbit perturbations, it would deepen the mystery, suggesting either a different internal structure or a surface process that defies current models. The properties of the dust within the coma will also be revealing. Observations of polarization at various phase angles, particularly post-perihelion, could shed light on the grain size distribution, informing us about the physical makeup and evolution of the dust. Spectroscopic analysis aiming to identify trace species, such as complex organics or noble metals, could further constrain formation conditions. If the signal-to-noise ratio improves, perhaps in mid-December of 2025, a promising window for detailed imaging will open, enabling high-resolution observations before the object dims and fades into the background star field. Looking further ahead, the best geometric vantage point from Earth will come before the object's brightness diminishes too much, providing an optimal moment for detailed imaging, possibly with one more JWST observation if scheduling permits. Radar observations, while unlikely due to the object's rapid departure and distance, could still be attempted if it comes sufficiently close. Ultimately, however, ATLAS will slip below the detection threshold, too faint, too distant, and moving too swiftly. And we will be left with the data gathered to date, along with the questions that remain unanswered. Now consider the timeline we are living through. We are witnesses to the discovery and initial characterization of only the third confirmed interstellar object in human history. Half a century ago, the very existence of interstellar objects was unimagined. 2 decades ago, they were purely speculative, predicted by models but yet to be observed. A decade ago, the enigmatic visitor Oumuamua sparked more questions than answers. 5 years back, Oumuamua's sibling Borisov reinforced the idea that interstellar comets might be common. Yet today, with 3I, the object in question emerges as something extraordinary, an object that defies easy classification. We are witnessing history being written in real time. Data are being released, papers published, hypotheses debated, and public interest heightened. In a few months, the chapter will close, ATLAS will have departed, and our focus will shift anew. But I want to leave you with a conceptual framework I call the originless frame. Perhaps in a universe that's dynamically active and constantly evolving, the stories of celestial travelers have fleeting lifespans. Maybe by the time we detect such objects, their origins have become blurred beyond recognition. Not because they are hiding, but because the galaxy's age and chaos ensure that information simply does not survive forever. Could the universe be replete with orphans? Celestial bodies that were not abandoned, but whose histories have been lost to the relentless march of entropy? 10 million years is an immense span. Catalogs are incomplete, and the cosmic record has been shredded by countless interactions. Now I invite you to consider one final speculative thought, clearly labeled as reflection, not claim. What if some objects in the cosmos are not meant to be traced back to their origins, but are instead better understood through sampling their compositions? What if the fundamental question isn't, where did you come from, but rather, what are you made of? In other words, instead of seeking a precise birthplace, perhaps these celestial wanderers serve as messengers. What if interstellar objects serve as the galaxy's silent messengers of chemistry, quietly dispersing and mixing materials across the vastness of light years, far beyond the reach of messages or probes? Not intentional signals, but grains of dust, icy fragments, carbon-rich particles, and water molecules, drifting aimlessly for billions of years, traversing the cosmic void. These travelers land in distant solar systems, seeding nascent planets, or instead escape into the darkness only to be caught fleetingly by telescopes operated by curious beings, apex predators peering into the abyss with wonder. What if Atlas isn't concealing its origins? What if, in truth, we have simply lost the trail? As the screen darkens, I want this thought to echo softly. Perhaps the interstellar visitor known as 3IATLAS never truly lost its past. Perhaps it carries memories we've failed to recover. Perhaps the Milky Way itself isn't merely an ocean, and Atlas isn't just a bottle cast into those waters. Perhaps the galaxy's tides have been flowing for 10 million years, carrying fragments like Atlas along their endless currents. The bottle is real. The ocean is real. But the shore from which it was launched, that's gone, washed away by time, smoothed over by entropy, vanished into the infinite drift of cosmic history.